Yeah. It's clean. No. Yeah. It's recording. It says recording. It says recording to the cloud. Should go. But it's not showing here. Maybe Errol is okay. It's okay. Errol can share. That should be fine. Yeah, I'll give introduction, but I don't need the slide. That's okay.
I'm here. Shall I share my screen?
Sorry for the technical glitches.
No problem.
It's a hybrid conference the first time, so I'll figure things out as we go. Well, welcome to the. Can everybody hear me at the back? Yeah. Okay. Okay. So it's the first workshop on machine learning with synthetic data. I'd like to welcome you all on behalf of organizers. As we know, large data sets are key to the success of machine learning model. And as we also know, collecting large data sets are hard and expensive. And you don't have to collect it only once. When the sensor changes or the test distribution changes, you may have to collect it again and multiple times. Sometimes it may be even hard to find the samples for the edge cases that you may be interested in. That's okay. Can you? Okay. We good? Okay. But with advances in simulation technologies, graphics, and generative models, synthetic data has become a viable alternative to real data. And the goal of this workshop, so at least one of the goals of this workshop is to discuss and explore the ways to reduce the ML model's dependency on the real data. And we have action-packed agenda. I wish I could share the right screen, but I guess I'm sharing the wrong screen in the room here. But we have 2 talks, 35 minutes each right now. And sorry for the delays. The time may not match what's listed in the website. Then we have a break of 15 minutes, and then we'll have 2 more talks. And then we'll wrap it up with a panel discussion. Awesome. And before we begin, we'd like to recognize and acknowledge that today is Juneteenth. It's a US holiday commemorating the end of slavery in the US and a holiday of special significance in the US South. I'd like to encourage everybody, all attendees, to learn more and explore its historical significance and join the city of New Orleans in celebrating this holiday. With that, I would like to hand it over to Errol Woods, who is a research scientist at Google. Errol, if you could try sharing the screen. I don't know how well it's going to work because we haven't done the tech check.
How's this looking for everyone? Is this looking okay? Oh, you're muted. I am guessing this is working okay. Is this
good?
Errol, we cannot hear you in the room.
Okay, and people can hear me. Oh, okay, awesome. So thank you very much for the introduction. Of course, I wish I could be there with you guys. Still, I'm very grateful for this opportunity to be able to present remotely. It's a bit of a shame I can't see the audience and all. I know one of my friends and colleagues, Stefan, is there, so I know there is at least one person physically there, so that's good to know. So yeah, I'm excited to be actually very soon starting at Google. Tomorrow, in fact, is my first day. But so all the work presented here was done at Microsoft in collaboration with the very talented and awesome team there led by Tadas Baltrushaitis. So this isn't work done at Google, this is Microsoft work. Just checking, is everything okay at your end? It looks like there's some sort of technical stuff going on. Am I good to continue?
I think you're not muted, Ashish.
I will press on. Let's keep going. So today I'm excited to talk about human synthetics. So as Ashish mentioned, when faced with the machine learning problem, the hardest thing these days isn't really choosing the right neural network, it's getting the right data. So I've worked on a bunch of human-related computer vision problems, and in many of them, synthetics has played a key part in landing the
I was
solution.
chatting with her.
And my goal today is to convince you guys that.
Please bear with us. It's technical difficulties. Figure it out how to get the sound.
Sorry, there's no sound coming through? Okay. I guess all you remote guys can hear me, but maybe no one physically there can.
By the way, if there's any Zoom expert in the room, we'd love to have some help.
Which channel you have? Okay. Aaron,
Hello?
I think we are here now. Okay.
So you guys can hear me over there in Louisiana now?
What I do?
Okay, I'll go ahead.
Okay, is working over there? I'll keep going. Okay, so I was just saying that my goal today is to convince you that synthetics not only works in the real world in production, and I think Ashish mentioned synthetics is a viable alternative to real data. I'm gonna show you that synthetics is better than real data. And once you can use synthetics to its full potential, you'll much rather make your data this way than try to collect it in the real world when it makes sense. So here's what I mean about working in production. So hopefully many of you guys by now will have had the chance to experience hand tracking on HoloLens 2. So that's this headset by Microsoft, and it's a magical experience that lets you interact with virtual objects much in the same way you would in real life with the real objects in new intuitive ways. What you might be surprised to hear, unless you've heard one of my talks before, is that a lot of the really hard computer vision here was trained with synthetic data only. So I don't mean that we mixed some synthetic data with some real data, and I don't mean that we pre-trained on synthetics and then fine-tuned on real, and I don't mean that we rendered some data, then did some sort of up-reeling stuff to it. This was fully synthetic, fully rendered data, and that's all the data these machine learning models saw at training time. And we deployed this, and it works pretty well. And so what do I mean by synthetic data? So synthetic data are labeled images made using computer graphics. And for me, there's three really important reasons why I think it's so great. So firstly, you can make clean labels without annotation noise or error. Secondly, you can create labels impossible to annotate by hand. I'll be talking a lot more about this later as well. And thirdly, it's easy to control variation in your data set. And these are all properties of having good training data. So what makes good synthetic data? So there are three things I'd like us to think about for this talk. So first of all is realism, then diversity, and finally richness of label. So first, let's go into realism. So in some ways, this is the most important thing to get right, in my opinion. So while many people have found success with less realistic data, so we're talking about maybe like some OpenGL rendered human composited over some random image from Flickr. I often worry about the domain mismatch here. So if your data is photorealistic, you won't have a domain mismatch, and people try all sorts of things trying to cross this domain gap. But I sort of argue that why should you need to do that? There's no reason why you can't render an image that is photorealistic. We go to the cinema, or we used to. We see Hollywood movies the whole time, and the 3D graphics there are completely convincing. And so I always like to try to push the realism side of things. And one of the reasons why this is important, I think, is that because graphics is all about approximation. So you might build a large synthetic pipeline around a certain level of approximation with a certain level of realism. And if you invest very heavily into that, it can be very hard to now crawl up the realism spectrum. If a lot of your assets and tooling are, have a certain level of realism, you can't sort of, say, oh, we'll invest 1 month and make it all more realistic. No, like you might be looking at retooling your entire thing, and that starts to become very intractable. So if you don't get this right early on, you can struggle to achieve realism later. Secondly is diversity. So good training data doesn't just mean loads of samples. Good training data must be diverse. And I think this is especially true for human-related computer vision. So humans look really different from one another, both in their size, their shape, the clothing and accessories they choose to wear. And in order for machine learning models to work well across the full spectrum of humanity, you've got to design synthetic data systems with diversity in mind. And it might be easy to simulate something like tight-fitting shirts and jeans, but you've also, if you want to deploy something in the real world, you've got to think about baggy dresses, baggy sleeves, this type of thing. And finally, it's a richness of labels. So there are many different human-related computer vision problems, and they require different types of labels. Sometimes it's fine just to have a bounding box, and whereas other times you might find you can solve a problem in interesting new ways with much richer types of labels like skeletal key points or even dense labels, which I think are becoming more and more popular. And it's especially it's labels on the far right end of the spectrum that synthetics helps unlock. So sometimes you want if you want this type of label, synthetics can give it to you for free with kind of the same labeling cost as a bounding box, which is incredible. So next, for the next part of the talk, I'm going to do a bit of a deep dive into one particular type of synthetics we worked on a lot at Microsoft, and this was synthetic face generation. So how do we make diverse, realistic synthetic face images? So the overview looks a bit like this. So we first start with a template face. So this is from our generative model. We apply an identity to it. We apply an expression to it. We apply it some skin textures. We put some hair on it. We put some clothing on it. And finally, we put it in an environment and render it. So let's go into each step here one by one. And we repeat this 100,000 times or so to make a data set. So we have a face model, and this is a generative face model, and these are really popular these days. If you've seen Flame, you'll be very familiar with this kind of formulation. We're talking about a linear blend skinned face rig that also has blend shapes for identity and expression. So I always, in general, like to buy rather than build. And so we thought about using Flame for our synthetic faces, but we found it didn't look quite as realistic as we wanted, especially for super close-up renders. So we did end up building our own. And this was designed from the ground up to be suitable for synthetics, to play well with graphics tooling. Like everything is really very traditional here. There's no sort of graphics thing here that wasn't in a PlayStation 2 game or something. Kind of interestingly, maybe our model does include the eyeballs and the teeth and the mouth sock and the gums and even the tongue. So we wanted to have everything here you would need to render a realistic face. You can refer to one of the papers for the details of this, I suppose. Here are some examples from some identity samples. So these are random faces. These aren't real scans of people. And I think the diversity expressed by our generative model is quite apparent. And we learned this from around 500 or so retopologized 3D scans. Our expression basis wasn't learned, actually. It came from a vendor, so that was handcrafted, and you'll see a bit more about that later. But first of all, about this the training data. So we purchased this data from several companies who are really good at doing this sort of thing. So photogrammetry is, for a while, been at a very high quality for faces if you have the right technology and the right expertise. So these are really, really detailed face models but we must clean them. So we're interested in modeling the naked head, and that means no hair, no hairnet, no eyebrows, no beard. So, I mean, we would, love to shave people's eyebrows and beards off for these kinds of scans, but that's not generally possible. So we got to do that shaving as a processing step for each scan. So we have some very talented artists go in and clean all of these up before they get used as training data. So it's not enough to know about how faces look when they're still. We need to know about how faces look when they're in motion. So to do this, it's nice to be data-driven where possible. So we did collect a expression database that tries to capture human face expressions of lots of different types. So we're talking, over 100 people, and about 70,000 frames worth of expression data, and this is how we went around capturing that. So we first of all, we have a multi-camera rig, and for each camera we predict a bunch of dense landmarks in each image, and then we fit our face model to them. And I'll talk the second half of this talk about. I'll explain a bit more how we do that. This model fitting. What you can see here is we repeat this for hundreds of different people, and this gives us a lot of different expressions, lots of varied smiles, mouth opens, squints, winks, blinks, chewing, kind of a lot of different facial range of motions that we might want to render as our synthetic training data. So that's, we now have the shape of a face down pretty well with different identities and different expressions, but these blue heads don't look very realistic yet. So what do we need to do? So we have this collection of scans that have been cleaned, and we build these materials with them. So we don't have a generative texture model. We just take, we call it exemplar based. We just pick a particular person's set of textures and we apply them to the geometry. But we take special care to make sure that the face does look realistic when viewed really close up. And this isn't just because we want it to look good, because we are perfectionists or something, but because in Microsoft Mixed Reality, we care about headsets. We do need to think about kind of like eye tracking based applications where we might want to render an eye really close up and have it look realistic. Next up is hair. So hair is really complicated, and we spent ages thinking about how to model hair. And this was an example of where we looked at lots of different approaches in graphics. So card-based was very popular when we started doing this, especially if you wanted something to be real time. But because we wanted to err on the side of realism, we wanted to get the most realistic hair assets possible. So that means these are strand-based hair assets. So an artist has created these, and each one has 100,000 different hair strands, and that lets us model the diversity of human hair really well. So you can get really curly hair, really straight hair, and this requires a lot of working very closely with the vendors to make sure we get a good diverse set of hairstyles. So I think here we can see some more examples. So we have wet hair and frizzy hair, short hair, long hair. So there's a very particular type of 3D artist that's very good at just doing just this, and it's a massive effort to create this collection of stuff. So while all human faces are maybe quite similar, or have points of correspondence, hair is really uncontrollable. So we don't have a sort of generative hair model. Again, we just choose one of these styles at render time, and that's the hair that person gets. Almost there now. So we have to put clothes on this person. So even though we're just interested in the face, like clothes are often nearly always in the shot if you can see someone's face. So we have a large digital wardrobe of these clothing items, which were made in a very traditional visual effects style way. So we use cloth sim to drape these clothing items over a static body, and we don't simulate these at sort of render time, but they end up looking pretty realistic and stand up to scrutiny. And of course, we also need to have other accessories like headwear, eyeglasses, Also, face masks nowadays have become very important. So here you can see an example of, you know, one of our digital humans being dressed up with lots of different clothing and accessories. So the very last thing before we render it is the environment. So this is a very common technique, I think, in synthetics nowadays, if you're just focusing on a single object. So we use high dynamic range environment maps, which provide a really easy way of giving a background and also some realistic lighting also to the subject and the scene. So this is a great example of how synthetics is a data multiplier. So, you know, if you have one 3D model of someone and you have 400 different environment maps, you know, actually just by rendering that same model in different lighting conditions will give you really different looking images, which is great for machine learning. So if you want your machine learning system to be robust against different illumination, which it must be to work in the real world, then this is, you know, an example of how synthetics, it really enables that. For rendering, we use Blender, and we actually use Blender for all of our scene composition. So we use some other tools for authoring the assets, but for putting everything together, we use Blender, which is just great. And we use its cycles path tracer. So this is, you know, it's quite computationally expensive to render one of these images, but it does end up looking pretty realistic. And so we render on Azure cloud cluster, and so it takes, I think, I can't remember, but we could render maybe 100,000 images in 30 hours or something, which was an okay turnaround time to iterate on data sets. Here is a little example of what some of the faces look like. So you can see, you know, different accessories, hats, glasses, lots of different hairstyles. Sometimes they do look pretty weird. They make weird combinations. And actually, we might argue that's a good thing. So if it made, you know, people that only ever were smiling and looking attractive, then that wouldn't be a very diverse data set. We found it wasn't really a problem to have kind of unusual combinations in our training data. It maybe just made it more robust to humanity on the whole. So, of course, like I talked, that all of that was about, you know, how to make synthetic data. And of course, it doesn't matter if it doesn't actually work on anything, but, you know, the proof is in the pudding. Like we have a paper on this where we benchmark several very well-trodden face-related tasks, so face parsing or semantic segmentation or landmark localization, and we show that synthetic data is just as good as real data for these, you know, really well-trodden things. And, you know, for the last example, this is maybe more exciting. So it shows that for some unusual tasks where it might be very hard to collect real data, like if you're doing something with maybe like a new HMD or you're trying to design, then you can generate synthetic data, which will help you prototype a lot of your algorithms. So for the next part of the talk, I'm going to go back to something you saw earlier, so these dense landmarks. So landmarks, you know, landmarks are maybe, I don't know, like the top face-related computer vision problem people think about, maybe like, you know, near face recognition, and they get used everywhere, right? They get used for face alignment, for like face bounding box discovery and so on. And they're great, but, you know, there's lots of things about a face that you can't represent, especially like a face's shape, with 68 landmarks alone. So what if instead of 68, we could predict over 10 times as many? So, you know, 700 or so landmarks, including landmarks on the eyes and landmarks on the teeth. And this is exactly the type of training data you can, I would say, only reliably create with synthetic data in a feasible manner. So what can we do with these landmarks? So earlier you saw we needed to fit our model to them. So how do we do that? So first we use our probabilistic dense landmark regressors that takes an image and it predicts a bunch of landmarks with certainty. And then we do some model fitting. So we take our face model that you saw earlier and we do some very traditional model fitting with our landmark energy to make the model match the observed data. So this probabilistic dense landmark regression, this is how we, given an image, we predict landmark coordinates. And so often with 68 landmarks, this is done by heat maps, nearly all the time. And that wasn't going to be feasible when we wanted to predict over 700 of them. So this is our kind of what we tried doing instead, and we were almost surprised that it worked so well, was just predicting the coordinate of each landmark and also some associated uncertainty. So there are these two losses where one loss penalizes the CNN for being too uncertain, and another one penalizes the CNN for making a bad landmark prediction. And one of my theories is that maybe this only works so well for us because we have these really precise noise-free annotations. Maybe that's why we didn't need to use heat maps or confidence maps, but I think that investigation is for another time. And this is what the results look like. So the red landmarks are being predicted with high uncertainty, and the green ones are being predicted with high certainty. So this is great when you see something getting included, like this guy's face here, or like this lady's face when she's drinking out of a coffee cup. But otherwise, I think you'll agree that the landmark predictions are pretty stable. So there's no smoothing going on here. This is just frame-to-frame landmark prediction. So next up is fitting our model. And what's great about these dense landmarks, which are only possible with synthetic data, is that it's a really strong energy term for a model fitter to use. So often in 3D face reconstruction, people will want to use some other energy terms like a depth map energy term, or maybe even some photo consistency terms, which can be very expensive to evaluate, inverse rendering style things. But instead of that, we just use the landmarks as our data term. We have a whole bunch of regularizers that try to penalize unusual face identity, shape, and neck angles and stuff like that. And so I find this pretty neat. I think because we had such a tight coupling between our generative face model, our synthetic data, the machine learning we trained with that data, and then our model fitting, this tight coupling really resulted in a not to pat ourselves on the back too much, but like quite an elegant approach. And I think the results ended up speaking for themselves. So given in the wild images like this, the dense landmarks, I think, quite successfly captured people's identity and expression. And then the model fit also produced a pretty faithful reconstruction of the face seen in the image. So there's an archive paper about this where you can see some more examples and comparisons. But we were very excited to show that with just dense landmarks alone, we could outperform other approaches that use more complex illumination models and texture models and things like that. And so finally, our approach can be made highly efficient. So because we have this synthetic data with such consistent landmarks, it was feasible to train a much like a very lightweight landmark model. So this is like a MobileNet v2 architecture. And then with some very carefully written 3D model fitter, this thing can be made to run very fast. So this is on a really quite low powered commodity laptop on a single thread. So not using any multi-threading, not using any GPUs, it would run in real time, no problem. So this here's a comparison to some of the other really good 3D face trackers out there. So I think by using dense landmarks, which have come from the synthetic data, it's clear that the dense landmarks are consistent enough to accurately capture identity and expression. I think there's just one more comparison to come up. Here's a Jing, another one of the authors. So finally, sort of two messages I'd like to repeat again is that synthetics really does work. It's not something that I think for a long time I would go to conferences and I'd see people have slides up saying something like synthetic data is not as good as real data or something. But I'm hoping I'm starting to convince some of you that synthetic data can actually be much better than real data. Some of the results I've shown today would not be possible with real data. I'm quite happy to claim, or would be so difficult to correctly label that it would become intractable. So maybe if you come around to building a synthetic data pipeline, don't think about how you're going to mix it with real data, or don't think about how you need to, bridge this domain gap. Try to think about just making the synthetic data as realistic as possible, and then, seeing what sort of awesome ground truth labels you can create with it. And you might be able to accomplish some pretty cool stuff. So thank you very much for listening. And finally, if you like what you've seen here and are interested in working with me and others in Tabo's team, please do send us an email. Google's digital humans effort is growing quite rapidly right now, and we're always looking for talented scientists like yourselves. So thank you very much, and I'm happy to take any questions.
Are there any questions? Maybe we can take 1 or 2 questions.
I see one in the chat as well. Maybe I'll start with the one in the chat just because it's there. So this is from Andreas. So the question is, how do you know that the images that look realistic to us humans look realistic to the model? CNNs have been known to overemphasize texture. Have you had any issues with this? So it's, I think that's a very interesting question. And I think it's related to another question, which is, like, how realistic do you need to go? I think a lot of judgment comes into this. Something maybe I didn't talk enough about was how, as you can imagine, a lot of science and engineering goes into this kind of work, but a lot of artistic sort of principles as well. And on the artistic side of things, people must end up using their judgment about what looks correct. Artists have been doing this for millennia. They didn't measure things with rulers or something. They could draw something and they would say that looks right, this looks wrong. Sometimes that's how we had to end up choosing some sort of techniques over others to make our images look as realistic as possible to us. But maybe this is a bit unrelated to your question you're asking, is like, does it look realistic to the CNN? I would maybe try to sidestep that again and say, like, what does it mean that it looks realistic to a CNN? What actually really matters is downstream performance on the task you care about. So is it maybe like fingerprint localization or something? Like, that's something you can measure. You can't measure if something looks realistic to a CNN in any way. But maybe for your product or your device to succeed, it needs to function in a certain way. And luckily you can measure that. And so I would always argue for also collecting a lot of real data to evaluate these models. So I love to train with synthetic data. I don't love to test with synthetic data at all. I'd much rather have real data from a real scenario where we can trust that we're not overfitting to synthetics. Oh, you're muted. Sorry.
How about now? I don't think we can hear you.
Okay. Okay, we're good. Thank you so much for this delightful and inspiring talk. I'm wondering, I believe this face data set is publicly available in the sense that the images are publicly available. Does the data set include any guidance on obtaining the 3D models from the vendors that you worked with? And if one could obtain those 3D models, how much work and kind of engineering effort would be involved in like regenerating the images?
That's a great question, and one we've heard many times. Like, I think, like, and we would also love to release, like an executable, where you could actually generate these images yourselves. But the unfortunate fact is we don't own, and when I say we here, I mean Microsoft. So I've since left, but also companies doing similar stuff. But the companies like Microsoft don't own the rights to these models. Like, we cannot release these models that we've purchased the licenses for. So we purchased the rights to use these models, but we can't release them for free on the internet. And that would, of course, if we did such a thing, the companies we purchased them off would not be very happy at all.
Oh, of course, I'm sympathetic to that and the fact that Microsoft doesn't own the models, but is there like a tutorial to tell me, okay, I have enough money to buy them from the original vendor. How do I get them from the vendor? And then how do I regenerate the images myself if I, have enough GPU resources to do so?
I'd say the best tutorial there is the paper we wrote about it, where we shared a lot of the sort of pipeline and strategy involved. Because there's also still a lot of I wish it were just buy the model, then render it, but there's a lot of extra steps in between, and that is still the case, perhaps unfortunately, because this is such a complex computer graphics system. It's but the steps are listed. It's a massive effort, I won't lie. This isn't cheap, this isn't easy to do. Collecting good real data isn't cheap or easy to do either. I've never been someone to claim that this is a cheap, easy alternative to real data. It's really hard to do to do right. But follow the steps in that paper, build a massive team, get a big budget, and or maybe first of all kind of figure out what kind of problems you're trying to tackle as well, and then start from there. That's what I would suggest.
Thank you.
In the interest of time, only if it's a very short question.
Okay, I'll try. Yes, thank you for the presentation. Like, I have more technical questions. So I looked at the big grids of humans that you showed, and I'm wondering, how do you actually attach assets to the model? Like, for example, hair.
That is, a great question, and we solved so many different problems like that. And I think at every step of the way, we didn't invent something new. We just used something from computer graphics. So this is a computer vision conference. Lots of the problems here have lots in common with computer graphics problems, and these problems have been solved millions of times already in video games and movies. And kind of one interesting thing about visual effects and computer graphics is there's always kind of 10 different ways of doing something, and there's never kind of one right way. And as computer scientists, we might like to think, oh, it's nice, there's one correct way to do something, it's very neat. But there are many different ways of doing something like that. So for the hair, we have kind of like a hair geometry, it's called, that is deformed to match the template of the skull. That's one way of doing it, and we did it that way. But different assets are attached in different ways. Like things like hats and helmets are deformed in a non-rigid manner, because people's heads have different sizes. Some people have wide heads, some people have narrow heads. Glasses are deformed with a skeletal wig, much like the skeletal wig you get in Simple. So it has bones for the two legs of the glasses. So there isn't one nice generic uniform way of attaching clothes and accessories to humans. And of course, that's just like real life as well, right? Clothes and accessories and hair, they're all very different things. Maybe it shouldn't be so surprising that it's so complex to try and fix them all to one 3D head. Thank you very much. I think you're muted again. Ooh, you're muted.
Yes, but are we recording the Zoom? Because my machine are recording. Okay.
But is this
Okay.
gonna work?
Yeah, that's right.
Can you hear me?
Come closer and take your mask off.
In the room we hear you, but
Wait, but I need to share screen, right? Can you hear me? All right.
just take a look.
Yes, we can still hear you.
It's very unstable. Okay. Remote can also hear. Okay, this is doesn't. We should not touch it. It's like magic. Okay.
It works.
It's
But now the people see my presenter slides. How do I?
no, you're good.
But on Zoom.
On Zoom, people will see. And Zoom, people will see.
How do you?
Yeah, they see that. That Zoom presenter.
Are you sure?
I'm pretty sure. This is what people see on Zoom. Right?
Sorry for interrupting. I think that microphone is this one is touching the laptop and it's wobbling and like
Yeah.
sounds.
Let's move it.
Okay,
Oops.
that's what people see on Zoom. I don't think screen share is working, but low res. And low res is an option for that. Now it exits that for example. I think better now. Okay. And you see the presenter slide? Did you turn off the Wi-Fi? Maybe we should.
No, it's
Yeah,
okay.
it's okay. It sounds good. So it's good. We see we don't see your presenter.
You don't see the presenter? That's what you see? Okay, awesome.
You can introduce yourself a little bit. I didn't do a good job of introduction.
It's okay. All right. It's more challenging to be in person these days. I should have stayed in the hotel room and connect through Zoom. Hi, I'm Sanya, and today I'm mainly going to talk about the work that we have been doing at NVIDIA on neural 3D content creation. Oops. My controls don't work. Awesome. All right, so a lot of the applications these days are powered by AI, and some of them are more challenging than others, right? Both in terms of the complex system you need to build, as well as the safety critical aspects of it, right? So you need to reach really high performance. So there is a need for having various types of labels, right? You need to have ground truth at scale. And in some domains, such as self-driving or anything robotics related, you might also need a closed loop testing environment. All right, so we all know that the ground truth is expensive to get, or maybe even hard to get, right? So long tail events, even capture is hard, right? You need to have scouts going out and kind of find these really challenging domains that happen, once in a while. But in synthetic data, that's very easy, right? It's all in the hands of the creator. We can, design these long-tail events as you please. Sometimes the conditions in the world are making it hard to label, right? You have fog, you have snow, the visibility conditions might not be great. So, camera or other sensors might also not see the object. Again, in synthetic data, in simulation, all this comes for free. Oftentimes, of course, you also have occlusion, right? Dynamic scenes, objects occlude each other. And, in the real world, a human annotator would need to be guessing. And lastly, at least for autonomous driving, you have these sensors that only sparsely record the world. For example, LiDAR give you only sparse depth.
Sorry, they're still seeing the slide outline. Can we hit the slideshow? Can we hit the slideshow?
Yes.
The remote folks are still seeing the first slide.
Is it good now?
Okay, now works.
Now it's good?
Thank you.
All right. But with synthetic data, right, you don't need to, so you can actually create dense depth very easily because it's all just rendered in another channel. All right, awesome. So, this workshop is about synthetic data. And, today I'm going to talk about different approaches to generating synthetic data and also touching on simulation, which is a temporal and closed loop aspect of it. right? So I kind of think there's like 4 different ways, at least that's why we were approaching. One is graphics, where the artists need to create all this content of the world, of all the dynamic objects in the world, and then you need to have all these graphics and simulation and basically physics-based sensor simulation such that you can mimic the real world rig. There's another important thing which I think is going to be used more in the future, which is mixed reality, right? Because it's very easy to collect a lot of recorded data outside, right? The scene is kind of embedded in those videos, but you can actually add dynamic objects to this scene, right? And then obviously that comes with ground truth. Now in the mixed reality case, the scene was realistic, but it was kind of embedded. It was baked into the video. So we can go one step further with these neural approaches that people are working on these days, and make also the scene more editable, or change viewpoint and make it more manipulated. And the last way to kind of create synthetic data is using generative models, right? Where the hope is you train a generative model and you label only a couple of samples from this generative model, and then use the actual generative model to synthesize a lot more labeled data. So we have a bunch of works on this, including one at CVPR. I'm not going to talk about this last option today. Mainly focus on the first 3 options. All right, so let's talk about the graphics simulation or synthetic data creation first. And here NVIDIA is really well positioned in the space due to this really high performance, realistic rendering and physics simulator called Omniverse. So I'm gonna play this video. So basically, everything you're seeing here, dynamic lighting, all the physics, the rendering, which is photorealistic, everything is basically rendered in front of your eyes. This is Omniverse. And of course, this is critical for something like self-driving simulation, right? Where what you simulate needs to be as reactive and as fast as if it was in the real world. Maybe even faster if you really want to simulate faster than real time to be at scale. So NVIDIA Omniverse is basically this collaboration and real-time rendering simulation platform where you can connect all the existing 3D modeling tools, Blender, Maya, so you can create your content, whatever you want, but then use Omniverse for rendering. And the next cool thing is that you can very easily plug in technology. So if you have an AI, it's very easy to plug it into Omniverse with just Python interfaces, which is basically where we're going to come in. So one of these extensions is something called Drive Replicator, which builds on NVIDIA's driving simulator, but then you can also create randomized scenes, randomized content, and basically stream all the ground truth that you want. Let me just give you an example. So the first thing you see is Drive Sim, which is closed loop simulator. Very easily, right? Because everything is being labeled and manipulated. You can also create 4D labels for the ground truth for free. So semantic segmentation. So this can be used for training as well as validation of perception models. And because this is all graphics, it's very easy to simulate weather. You can have fog, you can have snow, rain, so everything can be randomized and controlled. All right, so the synthetic data generator, it's called a replicator. It's fully programmable, so you can actually bring in your own content, you bring in your own domain randomization, how you're gonna actually create these scenes, your own sensor models, and the type of ground truth you wanna create. All right, today I'm gonna focus on, what can AI do to actually enhance all these simulation capabilities. And we're gonna present a couple of tools that my team has been working on at NVIDIA. One, I've been talking about it a lot, so I'm just gonna kind of quickly browse through it, is auto-tuning procedural parameters of the scene generator, right? So if I go backward, here someone had to write a domain randomization engine, and that's typically based on some procedural model of how scenes are being generated, right? Where the creator needs to decide on the density of the scene, so how many objects you're gonna place, and then how you're gonna place them. So attributes like, how they're aligned, cars are aligned with the road and so on. So basically here, we want to kind of take the creator out of the loop and automatically tune all those parameters. I'm not going to go into the detail how you do that, but the basic summary is that even if you start with something as bad as the bottom left, which is a completely random scene, so this the creator would just say, generate very few objects, I don't care about how they're positioned, you can actually automatically tune this simulator to have the right density and the right attributes for the objects, and drastically improves performance in the end. And in this case, we're basically training or tuning this parameter such that the render data is actually matching the real world data, which we assume is completely unlabeled, making this just a plug and play, press the button and everything, the simulator is gonna adapt to the real data. Now, if you do have some annotated scenes, then maybe you wanna go beyond procedural modeling. Maybe you wanna create generative models of scene, right? They kind of try to mimic the real world data you're trying to model. So this was in collaboration with Andreas Geiger's team at the MPI. We basically have this transformer-based generative model that can condition on the layout, so either an indoor layout of the apartment or let's say an HD map of the outdoor scene, and then completely synthesize these scenes automatically. You can also do completion, so you can click here I want this object, here I want this object as a constraint, and then the generator is going to complete the scene. Or you can just basically, say what should be inside this box here. So basically some sort of object suggestion. The nice thing about this model, it's super fast. So compared to previous models that take about a few seconds or even longer to synthesize a scene, like a really large scene here would take 200 milliseconds, which is fast. A couple of samples. So this is randomly sampled from the generative model, completing, and suggesting an object. And right now we're repurposing this for outdoor scenes. So you're gonna be able to basically synthesize a city, assuming you have a map. Nice thing about this model is actually generalizes this really well to floor plans that haven't been seen in training. So in this case, on the left side, you see a scene layout. So that's the floor plan. That looks really different than anything we've trained on. And these other models have trouble kind of following that, but we can actually create really nice scenes even in such cases, which I think is really important once we actually go to the scale of simulating a city. All right, the other tool that is really important is actually mimicking the real world data, right? So that means that we have recorded the real world data and we want to reconstruct the scenarios that actually do happen in the real world and then randomize them. So imagine that this is a real world scene that I want to reconstruct in simulation and graphics engine, right? So I want to be able to come as close as possible given the assets that I have to the scene I captured with the purpose of generating variations. Imagine that an issue happened in the real world, so then I want to basically generate variations that are going to help me train my model to be better. So here what we're doing is taking the original clip, detecting all the objects and their attributes. And on the right side, you're seeing basically what a relatively decent 3D object detector and tracker would do. Now, what you can see here is that actually a lot of trajectories kind of disappear in thin air, right? Because there's occlusion and so on. So here we're using an AI traffic model with a latent space to basically extrapolate all the trajectories that disappear to continue moving forward in a realistic way, and also basically simulate backwards, so where each of these objects originated from. So you can go and have a synthetic scene that looks realistic, so objects don't just disappear into thin air. So this would look like from the ego view. All right, awesome. So this was reconstruction. This is the first part of the tool. In the next tool, we actually want to create plausible variations. And not just plausible, we want to create challenging situations, because that's what's matter for a safety critical application, right? So we can take this regular initial scenario. And now what we're going to do is take any of the agents in the scene, and we're going to try to modify its trajectory such that it interjects with the ego car. Okay, and because we have this traffic model with a latent space, we can just do gradient-based optimization to find a new trajectory that's going to do this maneuver. Of course, there's many trivial solutions to this problem. So you want to make sure that there is an actual solution for the ego vehicle to avoid this collision if it was planned this way. I'm not going to go into more detail, but the work is going to be presented here at CVPR by Davis. Here is an example on the top left. So this is what the adversarial scenario would look like to cause this collision. And here it's in the bottom, where now the green car is able to successfully dodge this, which means that this is a plausible hard scenario. All right, so let's look at how these variations now would look like in a graphics engine. This is the first one. And of course, we can do that with any agent in the scene and create tons of different variations. And because we're in a graphics engine, we can also randomize weather, make the floor wet, and so on. So we can create like really interesting data. All right, let's talk about kind of what's the future of content creation, right? Everything right now is kind of depending on artists creating this content, right? So I took one snapshot of this reconstruction, which was like a few minutes long. And this is a snapshot with a scene that has quite a few cars inside. And if you look closely, there's actually a repetition of the same asset. Actually, it occurs twice. Why? Because even if you have a few hundred models with a scene that has 50 different cars, the chances of getting the same asset back using retrieval is quite high, right? So we want to have some more variation in our assets, right? AI should do this heavy lifting as opposed to people doing it. So imagine this is the original asset. So typically what people do is completely annotate this object. They would say, this part of the car, in this case, is part of the asset, could be randomized with this kind of textures or colors. And they do it for every single segment of the car, which obviously takes a lot of time to prepare this asset for downstream randomization. So here we just want to create many appearance variation using AI. So all you do is take the original asset, another asset where we're going to kind of take the texture out, and we're going to place it on top of this asset. So you can see that you can generate pretty nice, plausible, retextured vehicles here. A few more examples in the bottom. So basically, the same texture applied to different models. At CVPR, you can check how it's actually done. It's going to be presented this week. A couple more results for heads. So in the top, you have the texture source, and then we're going to be transferring it to different head models in this case. So it's not imperfect. It's not perfect, but I think it's getting pretty close to actually being used in practice. Here it's more challenging because animals have a lot more variation than heads, and it still does pretty well. And chairs are particularly challenging due to its challenging structure. All right, so this was just basically conditioning a shape and then swapping out textures using AI. But obviously, we want to be moving towards generative modeling of 3D content, right? So ideally, what we want is just take some noise vector, maybe one for shape, maybe one for texture, and generate a 3D texture model, right? And here, I'm quite a big believer of actually generating explicit representation of the content, because then you can plug it into any graphics engine, right? So we want to be generating mesh, texture, material properties, and be able to handle arbitrary topology and genus of the object, and possibly train this model from imagery, because that's actually available at scale. So I'm just going to show you a couple of very early results here, not published yet. All this is generated. Synthesizing is directly a 3D model. You can directly plug it in Omniverse in this case. Here we're interpolating the middle shape between the shape and the left and the right. And that's maybe one way to create different variations. And we also generate materials to get nice reflections in this case. Stop me whenever I'm done. Here is animals. Let me just move a little bit forward. because now we can also control it with text. You write in the bottom, you know, want a rusty car or a burnt car, and you can get, you know, pretty nice actual 3D content out that way, kind of like DALL-E, but for 3D content. Not that you're gonna find it in a driving simulator, but. All right, the nice thing about like having everything with a generative model is that you can actually find hard, challenging visual examples that way too, right? So on the left side, if I just sample a latent, in the bottom, you have mask Gaussian and output. So the segmentation looks pretty good, right? But now because the content is differentiable, it's all in this generative model, I can start optimizing for the latent code to start fooling mask Gaussian and in the end. So here is basically just a few steps of optimization. You get a model that's already producing completely wrong segmentation out of mask Gaussian, which is nice. I'm gonna skip this part. How much more do I have? 10 minutes? All right, awesome. All right, so the next thing that I wanted to mention is mixed reality. So in this case, we just want to take videos that have been recorded already and be able to insert objects into the scenes. So basically for this purpose, we want to estimate lighting of the scene correctly so that we can take a synthetic model and insert it correctly. Right, so here we have an input image. We want to be estimating lighting, which in this case is it has a volumetric representation. So you have this volumetric grid where each cell of the grid has a spherical Gaussian that models view-dependent effects and an HDR sun representation. And we're training this semi-supervised from the data. So the lighting representation, the volume is trained unsupervised with just reconstruction losses. And the sun, for the sun, we actually have some supervision. And everything is fine-tuned with differentiable object insertion. So you basically use this estimating lighting to insert an object into the scene, and then you have a discriminator judge whether it looks good or not, which basically gives this final nice gradients back to the full model and creates nice effects. So these guys here, the objects have been inserted into the real scenes. And we've also had some small experiments where you take new scenes, actually in this case, just 10% of new scenes data, and just basically place, in this case, construction vehicles and maybe a couple of other objects, which comes with supervision or ground truth, and we show that you can improve performance quite a bit just as a result of that. A couple more examples. So these are again construction vehicles. We're also estimating depth, so you can have this really nice effect where you can hide a car behind another car and still, you know, respect occlusion. Oops. And here is a couple more examples. So here is the right, is the construction vehicle. Here I want to put some garbage cans on the right. Here we're using Omniverse. You also have free physics. So you have this car with a traffic sign. And you can also swap objects between different videos. I'm going to talk a little bit later about how we do the reconstruction. But with the help of AR, you can basically, you know, reconstruct content from different videos and then swap and replace them into other scenes. And just notice the shadows that you get in each of the videos. And of course, you can also add other dynamic context, such as pedestrians. Awesome. All right, so now let's move to the final part of the talk, where we actually want to also reconstruct the scene and have some neural simulation of the scene and allow closed loop simulation, meaning that the ego vehicle can now also take an action in this environment, a constructed and completely neural environment. So basically the goal is going to be take a drive, something like this one, where there's this dynamic object, dynamic car approaching us. And each of the videos, of course, has these recorded actions that the vehicle took when collecting the data. And now we want to be able to basically take new actions, make this a simulator. So turn all the recorded data that we have stored somewhere we want to make them into an editable and closed loop simulated environment. Pixel perfect. All right, so before we were doing retrieval and going into graphics content, which is never perfectly reproducing the original drive. Here we actually want to do pixel perfect reconstruction and simulation. So there is again a couple of tools that we need to use. One is scene reconstruction. So first we're gonna remove all dynamic objects and just focus on reconstructing the static scene. And we're using the NVIDIA super fast instant nerf for this with some additional tricks for quality. And we're also getting really nice geometry, and we need geometry because for simulation, you need to place vehicles on the ground in order to estimate all the physics effect of traveling. So here is just reconstruction on a bit larger scale. And again, we're completely changing the camera from its original trajectories. And you can imagine, even though you use the car to collect the data, you can simulate a test time like a mouse or even a quadcopter that flies quite low. All right, so initially we just removed all dynamic objects. So now we want to put them back and make them editable, all right? So for this, we're gonna use a multi-view object reconstruction approach where we're gonna use explicit prediction. So we're gonna take these multiple views and predict geometry, so a mesh, texture, and as well as material, so we can actually simulate nice lighting effects. And again, this is an oral TVPR. You can hear about it this next week. So in this original scene, this is our reconstruction. We're gonna place this vehicle back in its original trajectory. It's gonna drive, and just notice the nice lighting and shadow effects we can get just because of this decomposition and the AR capability. All right, there's also traffic modeling. I don't think I have time to talk about that. So I'm just gonna show you what you can do in the end by putting everything together. So all the objects are now reactive, and you can make novel actions, and the dynamic objects are going to be reacting to you. You can add synthetic data, and we're also simulating other sensors that I haven't talked about today, which is LiDAR, for example. All right, great. So hopefully I convinced you that there's different ways to simulate content. In my opinion, we need all four of this to actually solve such complicated problems such as self-driving. And in the end, I would just like to give a shout out to the team that has worked really hard on everything we've seen today. Thank you. Did you hear this? It's very hard to hear you. I'm really sorry. Yeah, it's here. Yeah, I'll repeat it. I just didn't hear. I'm really sorry. Sure, go for it. Yes, it's a really good question. So the question is, what are the effects that we can't really simulate today? So basically the gaps where all this scenario construction and simulation fails. And then, if there's any way to improve that in the future. Yeah, so you saw a very simple scene here being reconstructed. So obviously there is tons of gaps still, right? One is if you have a complicated scenario with tons of vehicles, pedestrians. Right now, if you watch closely, the pedestrian gets wiped out and we don't insert it back. We're working on this, but it's gonna take some time to make that as realistic as for cars. The other thing is just effects, weather effects, right? So for example, fog, snow, any kind of effects like this would, right now, I have no hope of this working. I think NERF could actually potentially work, but the 3D reconstruction that we also need for simulation, I think, would not give us good LiDAR simulation. So how to improve that? Well, continue working on this, right? There's a lot to still do. I don't have a specific answer. Thank you for the question. There's a huge echo and we don't hear it. Why don't you try? And otherwise, we're going to have you come here. Oh, okay.
That's really great. My question is related to so for creating all of this 3D content, like cars, humans, you need like a lot of images, right? I'm wondering what about the objects which are like in the long tail? So you have like very few images of some objects, and you showed like some of the cranes and stuff which you might not find like a lot of data for. So what do you do for such in the wild objects with like few images?
Very good question. All right, so the question is, how do you reconstruct or generate objects at the tail, right? So for example, construction vehicles or maybe some very, content that you don't really encounter in the real world. So the reconstruction, the multi-view reconstruction approach could actually reconstruct construction vehicles if you encounter one in the world. I would say that synthesized, so a generative model of the long tail, it would still be hard, right? It has all the problems that the regular GANs have, which means dropping the tails, which I think maybe with these diffusion models, maybe we're going to move more forward in this direction. Then content you never encounter in the real world, well, we're still gonna need artists for that, right? So if I drive in Toronto, there is no hippo on the road, right? So I can't reconstruct one. In this case, I need to go to artist content, maybe learn from all this content that's available on marketplaces, right? Where maybe it's few of them, it's gonna be fuchsia generation, but maybe that's the next opportunity. So it's not going to work today, but it's a nice opportunity for this 3D content creation. Thanks for the question. Okay, long question. But the main point was I was showing these adversarial examples, which were not really considering perception, right? So they were actually attacking only the planner part. So creating accidents that would be hard for the planner. Once the content actually becomes differentiable, then you could actually jointly optimize attack, maybe even an entire system, but definitely planning and perception. I think the second part of the question was how do you go into really the long tail, right? Not taking something that occurred on the road and then tweaking it. How do you actually go into these really long tail events that you maybe never capture in the real world? I don't have a really good idea for that other than just, it has to be created by humans maybe, right? That has this experience and maybe have seen that or kind of have a good common sense of what could have happened and then create it in either the graphics or in some sort of a mixed reality setting. But sorry, I don't have a perfect answer for that yet. Thank you very much. I'll stop here.
Okay.
Test.
But it's fine.
There is no more. Okay, there is already.
That right?
Yeah, chat.
We are going to start in 2 minutes. We have two very exciting talks in the second session, and we will have a panel session with our panelists.
Hello, welcome back. Next, we have Jonathan Lesson. He's the head of AI research at DataGen. Jonathan, take it away.
Hi, can you hear me? Excellent. So my name is Jonathan. I'm the head of AI research at DataGen. And here we go. I'm gonna talk a little bit about what we're doing at DataGen. I'm really happy that Errol Wood had the first talk today, unexpectedly so. Because a lot of the work that we're gonna do is kind of corresponds with his work at Microsoft. So DataGen is a young company. We're about 3 or 4 years old, about 100 employees. We have offices in Tel Aviv, New York, India, and with a lot of support. And we're in the business of generating synthetic data to train AI algorithms. So we generate simulated images. In this case, you can see simulated faces. And then, and if you've seen Errol's talk, you've seen a lot of, we've seen an example of the benefit that you could do with such images, if you can have such images. We don't just focus on faces or still images. We also do videos, anything that generates people and people interacting with objects. And we produced images of these people interacting with objects in the right context. So for example, in-cabin automotive, smart office, conference rooms, home security, if you want videos of people putting, acting or putting boxes outside your door, and recently smart fitness. Can you hear me okay? Oh, awesome. So.
There is same video.
Ah, nice. Thank you. So this is an example. 1 second. Yeah. So this is an example of photos from our video domain. And of course, we do video as well. Our photos are generated using a graphics pipeline with the very high quality rendering. You can see the effect of the ray tracing renderer on the floor with all the lights and reflections. And we specialize in making these type of videos for the purpose of training and detecting particular behaviors. But in this talk, I want to talk about, I want to focus on faces. And as you saw in the first talk of by Errol, 1 second. So you see this as well. 1 second, and somehow I need to get this cleared. Here we go. So I think the point of Errol in his talk and the point that we're trying to make here is that synthetic data can replace at least part, if not all, of your real data. Okay, and in his talk, he showed how, so the pictures of the left, the faces of the left are faces that were generated using the synthetic pipeline. Very beautiful pictures with faces with various ethnicities and accessories, hats, glasses, face masks, and all these things. And they showed in a bunch of papers that you can get to a level that is comparable to the state of the art on classic tasks like face segmentation or landmark detection. And you can do even things that you can't do with real data. For example, he mentioned the dense landmark segmentation, where instead of training a model to predict 68 landmarks, this is the classic task, they predict the dense landmarks, which is around 700 such landmarks. And because you have this, apparently if you have a model that can predict those 700 landmarks, then the next step that you can take is just fit the face mesh just based on these landmarks. And this created a new state of the art that didn't involve the highly computational cost of a differentiable renderer, etc. So synthetic data is great, but as other people asked here in the audience, how hard is it to get it? Even if you license it and you need to build all this graphics pipeline, it's going to be very expensive, and there are no ready recipes that you can just buy it, take it, and use it. Well, this is us. So our goal here is to give you what basically democratize the synthetic data sphere, and you don't need to, if you want to reach the same level of performance that you've seen in Errol's talk and other talks that use synthetic data, you and you and you, everyone here in the audience can become a client of DataGen and just use our platform to generate this level of synthetic data. So in this example, we're showing our face generation platform, where you can choose you can have full control over the diversity of the ethnic background, gender, male versus female. You can choose whether you want facial hair or not. You can choose which accessories to put, eye gaze distribution, and HDRI lighting, indoor, outdoor. You can have multiple images. So the scene, you can have it with multiple lightings. You can choose the exact capturing device. So you could actually decide exactly the extrinsics and the intrinsic of the cameras that you want your model to be taken. So you don't have to rely on some devices that they're not related to your own product. And then you can just click generate, and after a few hours, you'll get a data set. Sorry. Okay, so here are the examples of the faces that we generate using our platforms. And as mentioned, you get pixel perfect labels, you get the landmarks is the exact location, you get rich annotations that you can't get with hand labeled data, even if you try, like depth map, normal map. It's just impossible to get those by hand. And you get full control over the variation, over the diversity, and you can just engineer the capturing device, the cameras, the number of cameras, the angles, just the way you need. So in order to show that synthetic data can be used instead of realistic data, the first thing we try to do is to use it not for even training, just for testing. So we took 3 face data sets. So 2 of them were real data sets from real faces, and 1 of them is a synthetic data sets, ours. And we took DLib, which is a well-established algorithm for detecting the classic 68 landmarks. And we wanted to check whether the same biases that DLib has on real data can be observed on our synthetic data. Okay, so if DLib is better on males versus females, or DLib is better on white-skinned people versus dark-skinned people, you want to see whether you can see these red flags, these biases, just by applying DLib and testing the statistics on synthetic data. And unsurprisingly so, we found out that the same biases that are observed on real data, the statistically significant biases, can be seen on your synthetic data that was generated. So the problem is that in order to see these things on real data, you need to collect a lot of data to make the results statistically significant. You want this real data to do your training, to do to use it for for the training task, but not to use it only for evaluation. So apparently you can use synthetic data to do this evaluation and keep your real data for to use it for training for your tasks. So you see basically the same trends. The next thing we did is use the synthetic data for training purposes. And we followed the same approach that Errol showed here with Microsoft, and we did the landmark detection algorithm. And using 10,000 images of synthetic faces, we reached an NME, which is the average distance of the corresponding landmarks, of around 3.93, which is very close to what you can get using the Microsoft data, which at that point had a little bit more features like face masks and glasses, etc. Today, our platform has these features as well, so I expect the gap to get even smaller. And in Microsoft work, they also showed that if you're using 100,000 images, you get to even lower number, and all these numbers are very comparable to the state of the art that is used using real data. So let's talk a little bit about how to use synthetic data in order to achieve this type of result. So in order to use the synthetic data, you don't just get the synthetic data and hope that it will work on one shot. You need to do some iterative process. So we apply this data-centric approach when we generate, iteratively one data set and then another data set, and we zero in on the correct way to generate synthetic data that fits the problem. So in the first iteration, we had to, we generated the faces, we needed to fix the lighting. In the second iteration, we had to fix the location of the face and other aspects, until only at the 5th iteration, we zeroed in on the data set that proved optimal for this task. And when you add the real data and the synthetic data together, you can also see that you always get a boost. So here, the red line shows the performance using only real data, and the x-axis shows how much real data you're using. And you can see that no matter how much real data you have, using synthetic data always gives you a little boost. Of course, this boost is larger when you have small amount of real data, And it gets a little smaller when you have a lot of real data. But it always helps to get you a little bit of extra juice from your model. So crossing the domain gap with synthetic data, there's basically not just one gap. One gap is the photorealism gap. When you generate synthetic data, we can still tell that it's synthetic people and not real images. So, and as we said before, this is one of the most important gaps that we need to solve. But this is only one gap. Another one is the scene gap or the global gap. So as I mentioned before, when we did a statistic on the first data set, we realized that in the green dots here, you can see the statistic over the left eye of our original synthetic images, the right eye, and the chin. The blue dots represent the location of the left eye, the right eye, and the chin on the real data. So you can see that the real data was actually very well aligned, while the first iteration of our synthetic data wasn't. So we needed to adjust the crops of our synthetic data so that the location, the distribution of these landmarks under the synthetic images would be would support the distribution in the real data as well. And now we can get into some discussion whether you want it to be exactly the same or you want it even to be a little bit more robust to include even more extreme cases than the original distribution. But that's your choice. Another gap that you have is the augmentation gap. The images that we generate using synthetic data are extra clean. Every pointer was rendered exactly. There are no artifacts that were generated from a different set. There's no other noise unless we injected it there. So unlike the real images where there are compression artifacts, there's blurring, there are various ways in which the quality of the real image can be deteriorated. So unlike real images, when you generate data using synthetic engine, you do need to do heavier amounts of augmentation in order to get your training to be robust and useful. And last but not least is the annotation gap. So the semantic meaning that we give our synthetic labels, for example, we have the landmarks, then we put the landmarks at particular places. Maybe landmark number 34 should be the tip of the nose. When we check the real data, sometimes we see that the semantic meaning that we gave landmark number 34 is not exactly the semantic meaning that was in the real data. So maybe in the real data, that landmark is not at the tip of the nose, it's maybe a little bit down. So if you use the model that was trained on the synthetic data and just want to apply it on the real test set, you'll see that there's a constant offset between your predicted landmark 34 and the actual one. And this happens over and over, and you have to pay attention to this. So one classic example that also had to be dealt in Microsoft work was the landmarks that are on the jawline. And typically in synthetic data, we have a full 3D model. So the way we get the jawline landmarks is we just project them on the 2D image. So because we project them, they often cut the face in the middle, as can be seen here. While the human annotators on 2D images, they put the landmarks of the jawline on the contour. So one has to look at the predicted set of annotation that were used using synthetic 3D data and transform them to be to match the realistic to the data on the real images. And I know that both the Microsoft work and this work mentioned that we didn't use real data, but actually in order to do this level adaptation, we have to use real data. Because the way we do it is we take the real data, we run the model, the synthetic trained model in inference mode on the real data. So we get the predicted synthetic labels. And then for the same real data, we have the ground truth labels. And the way we do this level adaptation is by training a neural network. And the neural network's input is the predicted labels, and it needs to transform these predicted labels to the ground truth label. So it's actually not 100% accurate that those models that achieved the 3.3 and 3.6 NME didn't see real data at all. They actually used real data in order to do this level adaptation. And without this level adaptation, you wouldn't get these good results. You will get systematic errors. And this is also true for the way humans annotate these, the semantic meaning that humans give these landmarks. So even if we tell the humans to put the landmark at the tip of the nose, there's always going to be some noise. And in the jawline, as you can see here, there's much more noise in the human annotators. So this is the distribution of the human error. When you ask a few humans to annotate the same picture and you get the distribution over each landmark, you see that for some landmarks, there's a huge standard, there's huge variance. And for others is very accurate. So in the rest of the talk, I want to focus on maybe the most important gap, the photorealism gap, and think how we can how we can bridge that gap in synthetic data. So talking about a different model that I think bridges the gap between real and synthetic data is StyleGAN. I don't know about you, but unless I look really closely, I can't tell the difference between the images that StyleGAN 2 produces and realistic images. I have to look at very subtle asymmetries in the ears and stuff like that. Those images are photorealistic from my perspective all the way through. So is there a way to use StyleGAN to get our synthetic data to look as photorealistic as this? So StyleGAN is this is like this alien life form that landed in 2018, 2019, and there's a lot of work that after this alien has landed, just probe this model and try to get a lot of juice out of it, a lot of things that can be done with it. And the way StyleGAN works, just in general, is that you get this Z vector that is just 512 numbers. This Z is normally distributed, and it's mapped to another vector called W, which also has 512 numbers. Now, these W's here, these W vectors are replicated 18 times. So there are 18 layers in the StyleGAN that generates the image from low resolution to higher and higher resolutions. And each one of these layers gets as an input a replicated W. That W goes under some affine transformation, and eventually the image is generated using all these W's. Now, if you change the W that is given to this at the top of the StyleGAN, you'll see huge changes in the geometry of the face that the StyleGAN would generate. If you change the W at the bottom here, so you diverge from the replicated set of W's, you allow some changes, you'll see changes in the image that are not related to geometry. You'll see only changes in the lighting, changes in the colors, changing in other aspects, but the geometry otherwise is fixed. This space where the W's are allowed to diverge and not be replicated is called W+. And this space is very important if you want to be able to control what the StyleGAN is producing. So using this, basically having this StyleGAN alien landing on Earth, we have two different lines of research. One of them is StyleGAN editing. StyleGAN editing is about getting the Z vector and applying a particular direction that was pre-learned. So you take the Z vector and you add to it a new vector that was learned from by previous model, and that direction applies a certain edit, like opening the eyes or like moving the head a little bit to the right or a little bit to the left. And it's the same vector that you can apply to every Z that will create the same effect. So there's a lot of work that's been done on finding those edit vectors that do all these sorts of things to human faces. Another line of work is inversion. Out of the box, StyleGAN can only generate faces from random vectors. But if you have a face that was taken from the real world and you want to edit it using one of the pre-trained vectors, you can do it. You need to invert it into the StyleGAN space. So there's a bunch of work that was done in order to do exactly that. One of them, or the start, was, okay, we have this W here. We have the target image that we want to edit with StyleGAN. Let's find the W that is closest, that creates the image that is closest to this picture of Obama. This is an optimization process. It takes a few minutes sometimes, And eventually you get an image that doesn't really look quite like Obama. And the reason is that the space, the W space, is too restricted. It only has 512 numbers. If you increase the space to W plus and you allow the W's to diverge, you get a much better picture of Obama. But apparently, you can invert almost anything using this W plus space. You can take an image of a cat and take a stagen that was trained on human, and somehow you'll find the W's, the 18 W vectors that will produce this cat using a stagen that was trained on humans. So the W plus is a little bit too wild. Oh, and why is it a problem? The problem is that the edit vectors in this case wouldn't work. So in order for the pre-learned edit vectors to work, you have to have the replicated W's still be close to the original W space. They can't be too much different from each other. So there are other approaches that try to do this by putting regularization on the replicated W's. So you get to benefit from both worlds. You get a better accuracy, better inversions on one hand, and on the other hand, you're still able to use the edit vectors to produce the changes that you want. And one nice thing that you can do is you can train an encoder. So in all this paper, the stagen is pre-trained from the beginning. The encoder is actually learned, and the encoder looks at the image that you want to invert, and it learns how to produce the set of W's that the stagen will generate a similar face to. Of course, the advantage in using an encoder is that it doesn't take a few minutes to optimize. It takes only a few milliseconds because it's just a forward pass. Now, going back to our synthetic data, can we use those inversion algorithms to turn our synthetic faces to realistically looking faces? So in this image here, you can see synthetic faces that were generated using our platform on the right. And on the left, you see the inverted image. I don't know if you can see it if you can see the effect on the screen, but the image on the left does look a little bit more photorealistic than the one on the right. But the face looks a little different, right? Sometimes it's not exactly the same face. So there are these subtle differences. And the question is, can we make it a little even more accurate? So if you're using a combination of the two approaches that I showed before, optimization and encoding, then you can get a better inversion. What do I mean? I mean is that you take the encoder's set of W's as your initial point, and then you apply optimization for only a few seconds. If you do that, you can get an image. This is after using the optimization, and this is just using the encoder. You can see that the face looks much closer to the synthetic image. The hairline looks much better. The texture of the face looks much better. Here you can see that the color of the eyes is more like the original synthetic image. But then there is another philosophical question that we need to ask ourselves. If we do the inversion too well, then we'll get the same elements that made the synthetic data not photorealistic to begin with. So there is some trade-off here. So the distortion photorealism trade-off. On one hand, so here you see an example of a synthetic image, and on green you see the landmarks that was produced, the pixel accurate landmarks produced by the framework. Here you see the inversion into stagen space. And you can see that some of these landmarks have moved. So we sacrificed a little bit the accuracy of these landmarks in order to get the picture to be more photorealistic. It's important to pay attention to this. So if I wanted to fix those landmarks, I had to add new losses that will make sure that those landmarks are not going to move anymore. So moving to a different way in which we can invert, I told you before that if we change the W on the lower level of the style gun, then it doesn't affect the geometry of the face. So what we can do is that we can invert one of the synthetic images and then just play with the W's that are at the bottom, the ones that are closer to, after the image is already at closer to the full resolution. And then you get this amazing augmentation effect where we change the lighting, we change the hair color, we change the shirt color, a lot of elements that usually we can't do just by cropping and rotating images when we train images. And all these images would have exactly the same geometry because we only change the W's at the bottom of the style guide. Here's another example. Let's move over to editing. So I mentioned earlier that we have pre-trained vectors. Here we can take an image that was inverted, and because we inverted it using the right regularizations on the W, we can add glasses to the inverted image. We can make the person younger or older. We can move the hairline. Here we can make the person be either sad or smile, like here, move it horizontally, move it vertically. And it looks like the identity of the person, even though we didn't explicitly ask it to be the same, because we learned these edit vectors, the identity was actually kept. Only this particular effect was changed. In order to make sure that this is true, we applied FaceNet, which is a face recognition network. So FaceNet is a network that was pre-trained to provide a feature vector for every face. And those feature vectors for the same identity, those feature vectors should be very close. So we took one of the inverted images and we applied these edit vectors, and we checked with FaceNet how far each edit is compared to the original image. And the blue line is the median. So it means that 50% of the edits that we did, of the identities that we tried, were actually with a distance lower than this line. The other lines are for the 80 percentile and the 90 percentile of these changes. And typically, with FaceNet, a threshold of 0.4 and below, you'd say it's the same face. And above it, you'd not be so sure. So for most of these edits, indeed, FaceNet as well thought that this was the same identity, with a few exceptions. One of them is the horizontal changes. Apparently, when we change the face horizontally, especially in the extreme, to the extreme points, this is the left here and the right here, FaceNet begins to think it's not the same identity. And also glasses. Apparently, FaceNet is completely sensitive to glasses. You put the glasses on the same face, the same angle, the same lighting, and FaceNet thinks it's a different person. Of course, if we're training a face recognition algorithm, your glasses shouldn't make any difference. So that's what we wanted to do. We wanted to try to see if we can train a face recognition, improve FaceNet by taking a face recognition algorithm and augment it with this data that has images with glasses and without glasses to make sure that it can learn this type of invariance. So these are two inverted images, and we applied both augmentations and the edits that I showed you before to generate from each one of the inverted faces a bunch of other images of the same face that should have the same identity. And we used the same algorithm. We actually used ArcFace, which is the state of the art. It's slightly better than FaceNet to do face recognition. And we can see that even here, synthetic data makes a very nice boost all across the board. It's especially true if you don't have access to the original data. So the original data that the face recognition algorithm was trained on included something like 10,500 identities, and each identity had 50 images, typically low resolution images. So a lot of them, and we generated 10,000 faces, 10,000 images, and each one of them was augmented with 9 other faces. And the only reason we used 10,000 images is because at that time we only had 10,000 identities. As our platform gets bigger and better, we're going to have more identities, and we'll be able to show even better and better results because we'll have more diversity. And you can see that all across the board, and especially when you use smaller amount of real identities, you get a very nice boost just by using the synthetic data of around 10%. So to sum it all up, I completely support the conclusion that was made in the previous talk. The synthetic data can replace and sometimes can be even better than real data and be comparable to state of the art. But the domain gap needs to be addressed, and it's not just photorealism. It's the global scene parameters, it's the label adaptation that you have to pay attention to, and it's the noise and deterioration that you have to place. And also you need to pay attention to the photorealism distortion trade-off. if you want to make something more photorealistic and you want to invert it to the photorealistic world, then you're going to compromise something. And that something might not be aligned with your perfectly generated labels using the synthetic, using the graphics pipeline. Now, all this work was done by our very, very talented algorithm and research team in DataGen. If you're interested, come talk. We have a booth here. Come talk to us. If you like what you've seen, if you want to join us, we'll be happy to talk with you. Thank you. Yeah.
Here and ask this line.
I will. The question was, how does the Stagen inversion treat hair, and whether you get a better looking hair or more realistic looking hair compared to your synthetic images? My experience is that, yes, you do. So when you invert a synthetic image, even if the synthetic hair didn't look realistic, when you invert it, it will look more realistic because Stagen generated it. Yeah. So the question was whether the edit vectors have temporal consistency regarding the person's hair. So it's known that they don't necessarily, so you can't guarantee it. And that's one of the issues that you have with Stagen. So when you apply these edit vectors, there's also, you know, the aliasing effects. So the texture tends to be stuck together and then change in some way that is not really smooth. That's one of the things that Stagen 3 solves. So maybe if we invert those images using Stagen 3, we'll have better temporal consistency. Yeah.
Oh, thank you very much.
Thank you.
Next one, and the following ones you want farming, it's a recorded video, and in the meantime, the lines of stuff break and we at 4:30 for the panel. Uncanny project, I guess, video.
Hi everyone, my name is Raquel Hurtasun and I am the CEO and founder of Wabi. Self-driving is one of the most exciting technologies of our generation. It is really going to transform the world as we know it today. It's going to bring safety to our roads. It's going to enable people to move from point A to point B that now they don't have means of transportation. And it's going to really solve the supply chain and logistic crisis that we are all living today. Now, in order to really be able to bring this technology to market, we need to have a new approach, a new generation, because current approaches haven't solved it. This is the reason why I founded Wabi, to develop this technology with the people that we love to work with. I founded the company a little bit over a year ago. We have offices in Toronto and San Francisco, and we have the opportunity as well of having remote people working all over the place. We fundraised one of the largest Series A in Canada in order to be able to develop this technology. And we have the best-in-class investors, for example, deep technology with Khosla Ventures, logistics with ABC and Uber, as well as the Canadian super thriving ecosystem. We have a very differentiated technology approach from our competitors, which is AI first and is very simulation centric. And today I'm going to show you a lot about how we do simulation, this next generation simulation at Wabi. We are laser focused into bringing this technology to market, building a technology that scales from day one. And in particular, focus on L4 tracking, tackling this logistics problem that we are all immersed into, and with a model of hub to hub, so that most of the drives are actually on highway, which is easier to solve than if you look at robotaxis. Let's talk a little bit about how self-driving actually works. Typically, you will, if you look at any self-driving vehicle out there, it collects data from the sensors. This is showcased here with a LiDAR point cloud seen from the top. And typically, you will also have access to high-definition maps, such that when you perform localization, you can utilize these maps that give you a lot of information about the surroundings of the vehicle. This is important because it's really hard to see really far with current sensors, and having a map can help you plan the right maneuver. Then the perception system typically, what it does is that it looks at raw sensor data and is responsible for estimating where the different actors are in the scene. Then we have motion forecasting or prediction, where for every actor, we want to understand how it might be moving in the next few seconds into the future. We utilize all this information in order to be able to plan a safe maneuver that is comfortable towards the goal. And this is a process that typically repeats, every 100 milliseconds or so. Okay, this is in a nutshell how a self-driving vehicle typically works. Now, if we look a little bit into what has happened since the DARPA challenge, which is almost 2 decades ago, we've seen meaningful progress, and there's been some, interesting milestones. But when we look at commercial deployment, it's very, very limited to very small and very simple operation domains. So the promise of self-driving everywhere is definitely far from being there. Why is this the case? Well, the first thing to acknowledge is that this problem is really, really hard. And the reason why is that the driving problem is actually pretty nuisance in terms of that small variations in the input can result in actions that should be very, very different. For example, if the vehicle in front of us is slamming on the brakes, we should have a very different behavior that if it's actually just driving straight. Now, if we look at the number of possible situations that we need to handle, there is exponentially many. And not only this number is actually very large, but it turns out that many of those situations we are rarely exposed. Some of them we might need to drive millions, billions of miles in order to see it even once, right? So we have a very long tail, and most of the events happen very, very infrequently. This makes it like a really hard problem. As I mentioned before, there is meaningful progress since the DARPA challenge, but we haven't seen really solutions that can solve this problem at the scale, that can really generalize to deal with all these different scenarios that might occur. And in my opinion, the main reason for this lies on the technology that the industry is utilizing today, which is still very reminiscent to what the DARPA challenge looked like. Which basically it requires a lot of manual tuning, both in terms of the design and the processes to develop the technology in terms of the software stack, but also in the way that the industry is doing testing in order to understand where the possible problems are, and in order to verify and potentially make the safety case when potentially the system is able to be deployed without a driver in the real world, right? The main way that the industry is doing this is just by driving millions of miles of the real world. So this is something that doesn't scale, right? And the better that your system gets, the least, less situations you're going to be exposed, the less you know about whether you can handle some of these rare cases, right? So we need a different approach. In terms of the brain of the self-driving vehicle, Wabi has a very differentiated, unique approach that is AI first, meaning that we're going to be able to train the system end to end, but at the same time is modular and is interpretable such that we can validate and verify the system, which is something very, very important for safety critical applications like self-driving. Also, it's important that if, in the event of the vehicle doing something that is non-optimal, we can trace back into why the system made that particular decision. However, the automation, the fact that you can train end to end, enables you to really have a developer productivity that is so much higher than what we see in the industry, where in this manually tuned software stacks that are overly complicated and very, very brittle, typically landing a change will take a quarter, 2 quarters, where for us, we can make changes every single day. So the speed of iteration, the speed that you can get better and better models is a game changer in terms of having the ability to end-to-end train the stack. The other advantage is that you are actually directly optimizing for the system level metrics, which is what you care about, which is the task of driving safely, not about how your perception system might actually see all the different actors perfectly, which is not oftentimes not correlated with how well you drive in the real world. This approach is also very, very scalable and is capable of very complex reasoning. And in particular, we use a combination of deep learning, probabilistic inference, and complex optimization in order of, this is the combination of the different models that we see in our software stack. And the entire set can actually be trained together, which is very, very exciting, both using a combination of real world data as well as in simulation, in either of the two or in a combination of the two. And this results in an approach that is much more affordable than what we see out there in the industry, where typically, different companies have invested already billions of dollars and they are still very far from the promise of self-driving. So it's very, very exciting what we are doing in terms of the brain of the self-driving vehicle. But today I'm going to be talking to you about our simulation, which is the other very exciting key differentiator that is, a game changer in terms of where the industry is today. And this simulator is very important that we can use it for both testing the entire system, as well as in order to train the entire system as well in simulation. All right, so let's go over in more details about how simulation works in the industry, and then I will contrast into how we do simulation at Wabi. Today in the industry, like most players utilize not one simulator, but they utilize a set of simulators in order, to have like different tools to try to understand potentially where the system is not performant. And in particular, I will go over these three types, the three types of simulators that are more readily employed. The first type is what is called log replay, which I would argue that it's not really simulation, but typically it's called a simulation in the industry. So this is why it's here. And in this log replay, so basically you have collected data in the real world, whether it's driving manually or driving in autonomy. And then what you're going to do is you're going to replay that data and then see how your new system that you are under test is going to perform in terms of perception, prediction, motion planning. Now, the good thing about this is that you have access to raw sensor data that were recorded before. Therefore, it's very realistic. However, this system is not reactive, meaning that you are not really testing the consequences of your actions. And therefore, there is like very little information beyond perception that you can, or prediction that you can really get with this type of simulation, right? You're just replaying, you're just watching a video, right? So there is no understanding of how, for example, a chain of small mistakes can be catastrophic in your system. So this gives you, some information about, some potential issues or regressions, but it's not really a tool that will replace driving in the real world. The second type of simulation that is also very employed in the industry is virtual simulation, where the input to the simulator is typically a scenario that is an abstraction of a potential situation. And this typically will be bounding boxes representing the different actors, as well as their potential behaviors. And typically you will have a structured testing of, a set of scenarios that are testing certain capabilities of the motion platform, right? The good thing about this is that it's reactive, meaning that the actors potentially going to react to you. And as a consequence, you're going to see what is the effect as you are driving of the different actions that you make. For example, if you're going to go off the road, or you're going to get into a collision, or in a situation that is not desirable, right? With log replay, you can't get into these situations because you're just replaying data that was captured before, and most likely that was not a situation that was, too critical. Now, the problem with this type of approach of this simulation of being able to test the motion planner is that you're only looking at one specific piece of the software stack. Furthermore, the input is typically either perfect or with very simplistic noise, so there is no way that you can understand how errors in perception and prediction can actually affect the decisions that your motion planner might make. So as a consequence, this is used as a tool, but again, it cannot be a substitute for just driving these millions of miles of the real world. The third type of simulation that we see in the industry as well, this is typically more on research mode, not necessarily really used in production, but companies are starting to invest into having access to game engines and then be able to generate data for training perception systems typically. And these are virtual worlds built by artists that with game engines that render them and give you, for example, sensor simulations of cameras in this case, as well as automatic labels, right? In this case, semantic segmentation is shown with Carla Simulator here. Now, these approaches are not really scalable because humans have to create these virtual worlds. They are not very realistic, right? They look cool, but for neural networks, for our perception systems, there is a big domain gap, and they are lacking diversity because there is typically only a few assets that you will see in this simulator. Right, so the consequence of this is that they are prototypes; they're not really employed in production, and when you see them, the only maybe place where they might be useful is for like really rare classes. For example, if you want to get additional data for, say, emergency vehicles. Right. So what's happening then in the industry is that, well, as you see in this pyramid here on the left. There is use of simulation with all these different tools, but that's not giving you so much information about how safe your system is. And then you need to go to a closed course. This is the test track in order to further do testing. And since that is not scalable, right, because it's very expensive and you can only do, say, a handful of tests every day, then typically people rely on just driving millions of miles of the real world in order to see where possible mistakes are. This is very expensive, and this is far from being the safest solution, right? You shouldn't be looking at where potential issues are when you go in public roads, right? That's definitely not the best option. So with the next generation simulator that I'm going to show you in a second, that Bobby has, we can invert this pyramid, where now we're going to be able to really substitute the need for driving all these miles in the real world by having a simulator that is a single simulator that can really simulate the entire process, including the sensors, in real time, immersive and reactive manner, like with almost no domain gap, such that we can really test very, very extensively in simulation and really get a very good understanding of where the system performs well and where the system doesn't perform well. Then we can do a little bit of closed-course testing, and then our need for validation in the real world is much, much smaller than in the rest of the industry. So we really invert in this pyramid, having a much safer, much more scalable, much faster and efficient solution to get, right? Because if you wanna rely on just driving, miles in the real world, you're gonna need to drive so much in order to see a lot of those real events, right? While in simulation, we can just directly create in them, without waiting a single second. All right, so let me show you the following video of our simulator. Hopefully this plays with audio for you.
Ever think about what it really takes to drive? Probably not. We learn it and we just do it. We'll stop. Think about it. Driving is hard. We process things quickly, react instantly. Our brains do this so well, it's mind-blowing. At Wabi, we're teaching the brain of a self-driving vehicle to do the same, but even better. This brain is virtual. Picture lines of code, like the Matrix. We call it the Wabi driver. But it still needs access to experiences to learn like us. That can't happen entirely out on the road. It would take thousands of self-driving vehicles, driving millions of miles for thousands of years to experience everything necessary to drive safely. After all, there are many things that happen very rarely. We need another way. That's why we made Wabi World, our high-fidelity driving simulator, or simply put, the ultimate school for self-driving vehicles. Let's take a look inside. First, Wabi World reconstructs from real-life sensor data. We can automatically reconstruct objects, such as cars, SUVs, trucks, and more. It can digitally recreate reality as seen, or even modify it, to create an endless number of diverse virtual worlds. And we can do this across different sensor configurations, as though the driver were in a car, or even a truck. All automatically and at scale. We drop the Wabi driver into these simulated virtual worlds, and it can see and behave exactly as it would in the real world. Wabi World can then create traffic scenarios to test the Wabi driver and generate all kinds of variations. We can create scenarios that mimic a calm afternoon or morning rush hour, 2-lane interstates or 5-lane freeways, all while reacting in real time to the Wabi driver's behavior to create interesting interactions. It's kind of like playing a video game, where every action has a reaction. The Wabi driver makes a choice, traffic reacts. But unlike a video game, Wabi World can multiply and evolve scenarios infinitely. We can also evaluate how the Wabi driver performs in simulation and use AI to automatically generate challenging and realistic scenarios. Wabi World doesn't just test the driver to its limits, but also helps it learn new skills. Initially, the novice driver has difficulty in a scenario. But over time, Wabi World can be an instructor and help the driver get better. So ultimately, the Wabi driver will learn on its own to drive safely in any vehicle, in any scenario, anywhere in the world. Ever think about what it really takes to drive? At Wabi, we have. And Wabi World is our answer.
All right, so now that you have seen the video, let's look at how this is really done. So the first thing to think about is, what is the type of simulator that we need in order to really replace driving in the real world? So we need something that mimics exactly the same process, right? So it has to be like playing a video game where every one of our actions has a reaction of the environment. It has to be immersive, such that the input to the software stack is the same type as if it was driving in the real world. So we need to simulate how cameras, LiDAR, radar will have observed the world, the scene that we are currently driving on the simulator. As I mentioned before, it has to be reactive, right? So that we understand how our actions impact the potential behaviors and actions that we will do in the future. It has to be at scale, and it has to have all the diversity of real world driving in terms of the scenarios, in terms of the appearance, instead of weather conditions, etc., etc., etc. And the other thing that we need to have is also a way to automatically evaluate how well we do in the simulation, right? Because we want to be able to run millions, billions of these simulations, right? And the simulator has to be very efficient, such that it can mimic the real-time or near real-time behavior of if we were driving in the real world. Okay, so these are all the characteristics that we have with Wabi World. All right, where we have Wabi driver, which is in this case the software stack that we are testing. Right, we have a representation of the world state. Given this, we can simulate with the sensors that is given as input, right? As the vehicle that is observing the scene is going to decide on a maneuver, then we're going to move that vehicle also according to some physics and things, because what we intend to execute is not exactly what happens, when you drive in the real world, right? Then the different actors are going to react to our actions, and we're going to re-update the world state, right? And we continue to do this closed loop simulation. And then we can utilize the updated world state in order to understand how well our actions were as we're actually executing them. That's the evaluator that automatically gives us metrics of how well the system behaves. Wabi World is built on 4 key capabilities or components that are necessary to have all of these components together in order to really build this next generation simulation. On the center here, you have the ability to reconstruct every single environment, including the dynamic objects, as you're driving from raw sensor data. This is the way that you can get scale in terms of incorporating, as many virtual worlds as the world in front of you. We have the ability to perform sensor simulation, right? With, in this case, LiDAR as well as cameras. The ability to perform, to create scenarios, right? So that it can test, the entire software stack, and the ability to learn in simulation. Okay, let me give you a little bit of flavor of all these different capabilities. In order to build the virtual world, the industry is looking into using artists that by hand create the different assets. And then there is a little bit of procedural modeling, which is a very simplistic automation technique in order to replicate the world to create larger worlds. So there is no way that you can get diversity and the level of realism that you need with such an approach. Right? And artists are very expensive, humans are expensive, right? So we need something different. Our approach is to utilize raw sensor data captured by any platform that is driving using LiDAR and camera, and then from that automatically reconstruct, thanks to our AI algorithms, reconstruct the environment, including every single dynamic object. And we can do this at the scale for any situation that we encounter as we drive around the world, right? So this gives you the diversity, the realism, the ability to really capture the entire world. So this can be used in order to create a catalog of possible dynamic objects, static objects, as well as environments. And then we're going to create new worlds, new situations, utilizing this catalog as the basis. In terms of our sensor simulation, it's important that it has to work in basically real time or near real time, and it has to be like super high fidelity. If we look at what the industry is doing, typically they employ physics-based simulation that are very typically very slow or not sufficiently high fidelity, and they also put a lot of difficult requirements in terms of how much you need to know about every asset or the environment in order to be able to simulate any of the phenomena. For example, If you want to simulate rain, some of the simulators require you to actually model every single drop of rain, right? That's something that is very, very hard to scale. In Wabi World, we have a very different approach, which is we use a combination of AI and physics in order to develop a new generation of algorithms, where the idea is that the physics show or provide with a representation that is almost there, but not like enough realism. And then AI, that's the last bit, where basically converts that rough physics into something that is super, super realistic and has much less requirements in terms of what you need to know about the real world. Right, so this is much more scalable. So let me show you in this video here, our lidar simulation on the left, camera simulation on the right, and what we're gonna do is creating scenarios that are maybe safety critical by inserting actors that are gonna ask or are gonna require us to react in order to be able to safely drive in the world. But obviously we need to do more than just insert actors, right? We need to be able to just regenerate different camera or lidar locations and different self-driving vehicle trajectories, because we want to do this in closed loop. So let me show you how we can do this. So I'm going to show you first a single log that we use as input for our virtual world creation. And this log is just generally camera and lidar captured by just driving around. So you see us here driving around a street in San Francisco, right? And what we're going to do with this is we're going to automatically remove every single dynamic object, and we're going to create a 3D virtual world from the rest of the scene. And then we're going to resimulate how the vehicle, while performing different trajectories, would have observed this scene if we were to drive differently. Okay, so let's look at this. So this is now our camera simulation, right? That is has removed all the different moving actors, and now we can go and then do different configurations. For example, what if we were driving in a different lane, as you see, left to right motion, right? What if we were driving slower? What if we were driving with a different frame rate or a different camera characteristic than the original one, right? As you see, it's extremely realistic, and we can do this just from a single log. And we can go further, and then in this case, now we're going to simulate also perspective as if we change platforms, for example, from a car that was the one that captured the original scene to now if we have a truck, which is what for logistics we're actually working on, and how we will observe the scene in this particular case, right? So we can really generalize across very different viewpoints from the original capture in a way that we can create camera simulation that, as you see over here, is really, really realistic. All right, so I'll show you some examples of how we can simulate the sensors. Let's go into how we can create scenarios in Wabi World. And in particular, we want to create these scenarios, and they're going to be in 3D, and we can generate, the camera simulation, lidar simulation for any of these scenarios. But I'm going to showcase them with a different kind of a different depiction, so that there is not too much information in the screen here. Okay, so the scenarios that we want to create are such that we want the actors to be reactive, right? Because depending on our actions, they would have done something different if they were to drive in the scene. Right? So they have to be intelligent. So a core component of Wabi World is, the zoo of intelligent actors that we have. Then the way that we generate the scenarios is actually fourfold. In the industry, you see a lot of just scripted scenarios where they're testing specific capabilities. For us, you can easily create scenarios in a scripted manner, for example, in a programmatic manner, so that, in a few seconds, you can create, the scenario that you're interested in testing. For example, if you're a test engineer, right, or a safety engineer. But we can also create the scenarios by importing automatically from real-world logs the scenarios that happen, and then modifying potentially these scenarios like in this case, this actor in pink is modified so that the actors have a different behavior now. And then we can test, how we will have reacted if the actors that we observe in the scene were to do something that are different from what they did in the original log. Okay, so this is the ability to create reactive log replay, which is something that you don't see in the industry and it's necessary. What else can we do? We can also generate. We have, I guess, deep generative models of the multi-agent that can generate traffic situations from different traffic conditions to also how this traffic will be in different, we can generate different maps and different traffic situations within those maps, right? So this gives you the ability to generate an infinite number of scenarios with different situations in different geographies. Which is important for testing, for example, how well you can generalize your system. And the last bit that we can do is create the scenarios in an adversarial manner. And this is also very important because as your software stack gets better, you're going to pass most of the scenarios, if not all, right? And then you require more and more scenarios in order to find your issues, right? You can go from millions to billions, right? So this is computationally not feasible. Right. So what you need is a way to automate finding your mistakes. And we do this by creating adversarial examples where here the adversaries are the agents in the scene. Okay, and here what you can see is a scenario where basically somebody is gonna encroach very closely to us and creating a situation that is hard for in this particular software stack to handle. Okay, so this is the way that we can discover this automatically just by running the adversarial mode. And it's actually very, very simple from a technology perspective in the sense that we have the evaluator that tells us how well we do as we are driving in the different scenarios, and this is utilized by the simulator in order to transform the actors into adversaries, and then basically as a feedback loop, these adversaries learn what is difficult for us by just looking at how well we behave as we are driving in the simulator. So this is a pretty nice way to automate the entire adversarial creation process. And it's interesting that simulation is oftentimes referred or think about in the context of just software testing, but simulation is much more than that. One of the things that we use the simulator for is actually to have the hardware and software team to be working together in as a single team. So let me explain you this in the context of how it's done in the industry. So typically you will have hardware team creates say the next generation of vehicle platform, including the sensor kit, where the different sensors are and what they are. Then once this is created after the design and the fabrication, then the software team needs to adjust the software so that it's compatible with this new configuration. And this is a process that takes quite a bit of time, right? And then they have to validate this process by driving in the real world again by another couple of million of miles or whatever it is for that particular industry player, right? And typically what they will discover is that some of the choices were not optimal, and they have to make some changes and then go back and reiterate the process. Every one of these iterations typically takes between a year to 2 years. Right, so it's a very, very slow process. By using our simulator, what we can do is change this process fully so that hardware and software are integrated. And it's a very, very efficient process. So instead, what we can do is, thanks to our sensor simulation technology, we can test many possible hardware platforms in simulation. Select the one that actually performs the best in terms of system level metrics. Then that's the one that is going to be fabricated. And then we just need to do a little bit of validation in the real world. And we have a new hardware platform that is actually much closer to being optimal than if we use a traditional approach. And this is something that we can do very, very quickly in a couple of sprints instead of having 1 to 2 years. Okay. And the technology employed for this is something that I showed you before. I want you to look at the top part of the video, where basically, we capture, our virtual world with some sensors, right? But then we can regenerate the scenarios by changing, in this case, if you look at the top, from a viewpoint of a single lidar on a car to 2 lidars mounted on top of a truck, right? And then we can test the entire system, train and test the entire system this way, right? For this new configuration, before we ever build, for example, a truck. And on the bottom, what you can see is the same idea, but if, with one of the cameras that I simulated that goes from being on a car to being on the truck, right? So the viewpoint is actually changed from the bottom right to the top. Let me play it again. Where basically now we are changing viewpoint, and then we can simulate, our camera data to be super realistic this way. So this is a game changer in the industry. The last bit, right, is that we can not just, test, the safety critical situations and all the scenarios at the scale and interleave the software hardware process and work together. But furthermore, we can train in simulation. And the idea of training in simulation is very simple, is that every time that you are interacting in a scenario, you can basically, thanks to this evaluator, you can provide feedback to the driver, the Wabi driver, which is our AI system that utilizes this in order to rewire its brain every time it sees a scenario, every time it is actually playing in the scenario, right? Really performing its actions in the scenario. And we can do this in the cloud at the scale distributed, so that we observe, a myriad of situations at once. So this is very, very effective and efficient in terms of learning. All right, and what you can see here in the video is at the beginning, it's a very naive planner, so it can get into collisions. And as it's experiencing the scenarios, it's learning better and better policies. In this case, it's still not perfect, right? Before, it doesn't learn yet to accelerate in order to be able to merge better, but after it repeats a couple of times, actually learns that complex behavior. All right, so having this simulator really enabled us to remove the need to drive these millions of miles in order to understand how our system is doing, and instead we can do it much safer, much more with this much more affordable solution. So just to summarize, the promise of self-driving is really the promise of a better world, and it's going to happen, and it's going to happen, I would say, fairly soon. And it's very, very exciting to be part of this, revolution of really bringing this technology to markets. But we believe that in order to really bring this at the scale, you need this new technology. Today, I show you our next generation simulator that is, the best simulator out there, by far in the industry, which is really this missing piece in order to test and train the system. If you're excited, come and join us. We are hiring a lot these days, so please, shoot me an email, or you can see here access to our web page. Okay, in terms of jobs. This is all from me today, and hope to work with you in the future. Bye.
think it's muted. You're muted.
Okay, so I was muted. So Rabia, if you can put your camera on. Yeah, I'm unmuted. Do you hear me from now?
Yeah, we can hear you, except your volume is a little bit soft.
Can we hear them? I don't see. I think, Juan, can you speak?
Yeah, can you hear me?
It's very low.
Like add on the I like I mean what I like get it. It is you know whatever but like 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 there's as far as I
Can you say something again?
I'm now the test subject, I guess.
There is audio.
There is audio, but it's
Ashish, can you hear it?
Can you hear him in the room? Okay, Quan, sorry, can you try again?
Yeah, or is it my microphone that's weird? I'm not so sure. Yeah.
Okay. I somehow have a very hard time hearing him, but we'll try. We'll give it a shot.
Yeah, let's try.
Let's try that.
Javier is here, right?
Javier is here, but he's not. Let's see. Oh,
Okay,
yeah,
yeah,
here. Awesome. So we'll see how it goes because we, the hybrid panel would be a bit more complicated than planned. You know what we're saying? Okay. Can you answer closing remarks? Sure. Yes. Okay, let's start the panel discussion. So today we have 1, 2, 3, 4, 5, 6, 7 panelists. So welcome. We have Jonathan Masserson, head of AI research at DataGen, in the room. We have also Mike Roberts, research scientist at Intel. Sanya will probably join. I think she's just a bit late. And then online, we have Errol Wood, who gave a talk, staff software engineer at Google. We have Kwon Mo Yi, assistant professor at UBC, Ankur Anda, research scientist at NVIDIA, and Javier Romero, research scientist at Meta. So we'll try to alternate between questions in the room and online, and Arun online will moderate the questions. So let's see if you have a first question. If not, I have one. Okay. Okay, maybe as a warm-up, so we have seen beautiful talks today with a lot of impressive pictures, but it seems to me that in industry and academia, we are not yet using synthetic data at the full scale. And so the question is, what are the major obstacles and challenges that needs to be addressed for mainstream adoption of synthetic data? Maybe you want to try this one, Jonathan?
Yes. Can you hear me?
Yeah.
So, first of all, you need to have faith. I think a lot of people don't believe that synthetic data works, and we need our job in academy specialists to prove it to them. And I also notice sometimes that legal companies are actually not more convinced that synthetic data will work for them relatively to smaller companies. So because they already figured it out, like Microsoft, Google, Meta, they know it works. The smaller companies don't.
Do you think it's a problem of just compute and resources, or just a problem of belief?
I think Well, the other problems, just the first thing that came to my mind is to ask the question: what prevents the synthetic data to use in the industry is that the people need to be believe that they work, they need to be educated on the cases that they do work and when they work well. Also, it's just starting. Microsoft just released their results last year. We are quickly catching up and doing other things as well. It's not fully blown yet, and it's up to us to show that it works enough. I think after we do it, then we see more people in the industry adopt it.
Mike, yes.
Sorry for the other question. So the question was sort of what is preventing.
Like, what are the challenges that prevent adoption? Like, can we compute, other things, and how are we going to solve these challenges?
I think one of the challenges, I guess, is that the economics of synthetic data only make sense, or at least they only make sense to me for some problems. So the really gnarly understanding problems where it's really expensive to obtain like human annotations, that's where I think synthetic data makes the most sense. And not all industrially relevant problems are like that. Some, like real data is great too, and sometimes you can label it really inexpensively. And so I know on Hypersync, for example, it was between 50 cents and $1 for a regular image because I really wanted to spend as high quality as possible. And for some problems, you can just label your real data for cheaper than that. So I think that's a factor preventing the adoption. So I think if we can scale our library algorithms to
Maybe you can speak louder.
Reduce that computational cost and also reduce the content creation costs, doing some of the exciting stuff that Sonia was talking about. I think those are promising directions.
Awesome. Online, maybe Harold, you want to try with this one?
Sure, yeah. And what Jonathan and Matt have talked about, I definitely want to echo those concerns. In addition, I think it can be really hard to do well, and there's it requires a lot of interdisciplinary cooperation between kind of visual effects industry people who may be not so used to working with computer vision people and software and paradigms. So I feel like the industry has some way to come there with making that cooperation and interoperation a bit easier. And that's where, it's great to see companies like DataGen and Synthesis AI, try to bridge that gap a bit to, provide APIs and tools that computer vision people are comfortable with, which require way less on the graphics side of things. Can people hear me? Is the audio working at all?
Yeah.
Remote, yes. In person, who knows?
Okay, thanks, Errol. Unfortunately, it's very hard to hear you on stage, but I guess I know what you are mentioning. Let's see if we have some questions in the room. If not, we can continue a bit on this topic, or maybe online. Any question? Okay, let's maybe continue on this topic a little bit about one questions. Please walk to the microphone and ask a question. Go ahead. Oh. Working. Maybe you can walk to the stage and then we will repeat the question, if that's okay. Sorry about that. I don't think the online to hear you either. There's something with it.
So my question basically, what's the name away from the general presentation? So what's the main thing that needs to work now? But it's not working.
Okay, Ralph, sorry. Now you hear me? So the question is, in your approach, what are the tricks that make it work and why it was not working before? So what is really the key things that you did? You are me, Ralph? You are muted.
Oh, sorry. Was the question directed at me? I didn't hear the.
Sorry. So in your approach, what are the key tricks?
Got it. Yeah, there are so many of them. Can you guys hear me a bit better now, maybe? Hopefully. Can you guys hear anything?
I can hear you.
Yeah, we can hear you. I don't hear you, but people in the room can. So go ahead.
Oh, okay. Wow, that's
good.
You could just okay. Yeah, many tricks. Data augmentation is really important. I think Jonathan talks about it, especially with synthetic data. We turn the augmentation way up. It's kind of crazy what sort of horrible things we do to these nicely rendered images. So that is, of course, one type of bridging the domain gap. So we don't do anything really complex to bridge the gap, but lots of geometric and appearance style augmentation is really important. And I think it's diversity. So in lots of parts of the talk, I think I showed massive grids of the kind of different assets we had to build up, and it's a huge amount of effort by lots of talented artists and technical artists to integrate that sort of level of assets. And with some things like clothing and hair, it's very hard to make a generative model that is faithful to the diversity of what humans can exhibit while also being really detailed. So it's I think that's one of the key things that makes it really robust.
Okay, thanks. Maybe let's talk a little bit about quality and domain adaptation. So it seems that there's a bit a question about how much do we want to push the visual quality versus how much we want to invest in domain adaptation. And do we believe we can push the quality enough that we will never need domain adaptation? Maybe Anko, you want to take this one if you can hear me?
Can you repeat the question, please? Sorry, I couldn't hear you properly.
Let's try that again. Quality versus domain adaptation. Do we think we can push quality far enough so that we don't need domain adaptation?
I think the quality is certainly improving as we go with the high quality rendering that we're seeing, but it's very difficult to get everything in the simulator that you're going to get in the real world. So domain adaptation is certainly needed, I think, for various things related to the downstream task. I personally think this some of the things that I'm working on, I'm having to actually collect some real world data to make better sense of which knobs to tune in the simulator as well. And so this is certainly essential for any downstream task. Could you not hear me?
Yes, the room can hear you.
Okay.
Let's see if you have other questions online or in the room. Yes, there's one question. Okay, so I'll try again the question for you guys and online. So the question is, sorry, the question is, when synthetic beta become better and better, do we still need to do a lot of augmentation? And I guess by augmentation we mean probably blur and all these things, right? Or do we believe that like the amount of augmentation that we will do will reduce to better synthetic data?
So it depends when you draw the line. So if what do we call augmentation for synthetic data? So some of the augmentations that we do is actual noise into this data. So if you call this noise reducing the letters part of the platform, then maybe you want it to go any further augmentation. It's kind of going to be as part of the image that you're going to do.
Yeah, I guess it was more around domain adaptation, probably. Is that right? Yeah, more like domain, like machine learning based, like domain adaptation.
Well, okay, so doing like randomizing things in the rendering pipeline is an algorithm for domain adaptation. And I think we will still need to plenty of that augmentation, even if we have perfect quality synthetic data, because we still find that doing data augmentation is useful for real world data. So I would think it would still be more useful even with perfect quality synthetic data.
Can I say something?
Yeah, good.
I'm
showing my best.
No, those another things.
Sorry. You have a question?
Yeah. Did you hear the question? Can you repeat it for us?
So like he's working on hands. fetching the data to Crisp. So are techniques like style transfer useful? What do you do?
Style transfer in order to do what?
To make the data less crisp and more realistic, I guess.
Sounds like cool. Yeah.
I think that is a promising approach. In fact, Anshul has a paper on doing, I guess you could say, a form of style transfer using a GAN to make synthetic data have more sort of like real world-ish statistics. And I think that paper won best paper at CVPR a few years ago. So I'm bullish on techniques like that. You two should chat after the session.
Cool. Awesome. Let's talk a little bit about what I call semi-synthetic data. A lot of the presentation used actually real data at first, right? Like scans, facial scans, body scans to actually create synthetic data. So it's not perceptually synthetic. And this approach tends to interpolate. So the question is, how well do we think this approach extrapolates, or are we just confined to like the kind of convex hull of the scans? And maybe Javier can take this one, if he can hear me.
I think I could hear you. Can you hear me?
We
Or
can hear
maybe
you.
the room. Okay.
Yes.
So was the question about how much can we extrapolate from synthetic data that comes from scans or real data, right? Well, probably you cannot hear me, so I'll go with yes. I can talk about that. I think real data is a good basis for generating synthetic data afterwards. If you just take a set of scans to take your data set as is and you train your system with those scans, I don't think that typically is a good tool for creating systems. You would have to get tons of scans. Those scans come with noise. I mean, you would have to do a lot of cleaning and augmentation in some sense. But trying to distill the information that you have from those scans into models, classic or neural models, or clean those to create graphic assets that are used to expand afterwards. I think enable approaches like Errol's or somebody else's that go much more beyond what we've seen in the scans. No collection of scans that I've seen around is complete, especially for bodies. We've seen lots of work on faces. It is a little bit of a more confined space. For bodies, once you take into account pose and cloth, the space is huge. So you can definitely not encompass it all with a collection of scans. The hope is that you can combine it with synthetic data, simulation, with artistic input so that it extrapolates a bit better, and it definitely does. The ultimate question is, will it extrapolate to the whole population, all the clothes in the world, all the bodies? And that is a harder one. I'm not sure we are there yet to either scan all this data or even augment it. There are lots of challenges in that space to be really extrapolating into everything.
Thanks, Javier.
Can I add something? I haven't heard the solution, the
Yeah,
answer, but so I might be repeating what you said, but the question was whether everything we generate is an interpolation of this thing, the people that we scanned. So there's some truth to this.
Yes.
But we can break this by using 2D data. So, for example, Errol showed a work where they do face reconstruction by training a model on the by training a model on the synthetic dense landmarks. Then you can apply this model on FFHQ or some other face data sets, which is much easier to collect, like 2D images, and then you can break the barrier and create more meshes that don't necessarily are interpolations inside your own space.
So maybe I will ask the question again about what you are saying is, so let's say you train a model on synthetic data.
how well this model will extrapolate, meaning now if in FFHQ the data is out of the distribution, would then the ML model generalize and fit the faces that were not seen before if they are really not in the distribution? And if not, how do you detect then that these faces were not fit properly to, as you said, kind of bootstrap the system?
Are you saying that a model that was trained using synthetic data on the 3D models that we have is not going to properly find the dense landmarks on the 2D images because they were out of distribution?
Potentially, yeah.
Well, that's I think the paper that we had showed that that they all published there showed that they actually beat the state of the art in face reconstruction. So I think the variations that you're seeing when you apply this model into the model learns a lot from the 3D. You know, the things that you add using the simulation, maybe the textures and the lighting and all the robustness that you get from creating these rich 3D environments, that it is able to generalize to meshes that are not inside the scope of people that it's already seen. It becomes like a smaller part of the thing that it needs to learn because it learns each individual landmark.
Yeah. Still a question for me: how well does the model generalize and extrapolate, right, the distribution? I don't know, Errol, if you hear the question, maybe you can also comment on this.
Maybe you can hear me. I don't know. We found it kind of interesting. You know, we did, or some of my colleagues did run it on stuff like Pixar faces, you know, completely out of training distribution, and it worked pretty well. But that I would say is a happy accident. I wouldn't like to count on any model generalizing outside of the training distribution and sort of bet on that happening. Sure, it works. I have no idea why it works. I'm not, you know, comfortable with trusting that it's going to work on out of distribution test samples. So I think solving data diversity at the source in the training data is the correct way to do it. If you can use some great techniques of, you know, making really diverse training data that covers all these long tail scenarios correctly, that's the best way to go.
And if I may add to this, actually, I think it's this diversity issue is actually one of the strengths of using synthetic data. Like, for example, with synthetic data, you have control over what are the sort of the domain that you cover. And because in case of real data, data collection is always biased. You're going to be limited to a certain distribution. You're going to be biased towards some, for example, if you go around the world, collect cameras, collect images, a lot of the cases, it would be from a certain camera, right? So there's always a bias there. And actually, one of the things that I've done with physicists was to use synthetic data for simulating like spectral signals of astronomical images. And funny enough, they were actually keen towards using synthetic data and then creating a wide range of coverage and then using that to interpret real data. So in that case, perhaps synthetic data is somewhat more fair and unbiased in terms of getting your results. So actually, although we all know that ML models tend to interpolate well and extrapolate bad, using synthetic data might actually let you always be in the interpolation realm, which might be to your benefit.
I just wanted to interject with a follow-up question on that. Like, can you hear me?
Yes, we can hear you.
Okay, great. So you mentioned that, I mean, these models are great with interpolation, maybe not so great with extrapolation. Like, are there certain domains that we need to be extra careful about when applying synthetic data? For example, medical imaging. Like I mean, the data is pretty scarce there. And so synthetic data would be great, right? Because we can generate a lot more data to learn from. But how do we be sure that we are not generating wrong data? Like either interpolated or extrapolated, because that domain is, you know, there's no good simulator for the human. I mean, you can't get those medical images from a human body simulator. So like, is it GANs or is it some other procedural method? Like, what would you do?
So I think I can answer this as well because I actually have a paper creating synthetic tumors on CT scans. Actually, I was surprised when the medical professionals said this is an interesting thing to do, because I was like, okay, now I'm going to create synthetic tumor. There is no guarantee that this is actually a tumor, or this is actually even something that's going to happen. And I don't want any of that in my medical diagnosis, right? Of course. But what they said was, although this might be not useful for doing diagnosis automatically, it could be useful for perhaps trying to see statistically what's going to happen in the future with the current scan. Like, for example, how is your tumor going to develop? And those kind of case scenarios that are not as critical to diagnosis, these are still very useful things to get a sense of a statistical analysis of how things will evolve in a visual feedback that the doctors are very much used to. Like, because if you show them like there's 70% chance of this becoming a malignant or benign thing, well, that's not going to be as intuitive for these doctors than just showing there's 50% chance of becoming this, the other chance of becoming that. So this might actually be somewhat a hand-wavy answer, but sort of an answer to your question, David.
Thanks, Kwang. Okay, so there is one question online. So results were presented by the speakers where synthetic data was used in training to improve model performance when tested on real data. Can you discuss in general the training methods used? Pre-training on synthetic data, only training on synthetic data? I guess maybe Errol, you can take this one, as you were one of the speakers.
Yeah, so for the work I presented, we, ignoring label adaptation for now, it was purely training on synthetic data. Oh, actually, that's not quite true. We use pre-trained networks. I'm sorry. So, like we just said, give me a ResNet 50 with ImageNet weights or something. That's actually quite important. So, but for some reason, I don't consider this as a part of our training regime. It sort of seems like pretty good standard practice to use a pre-trained backbone. But for our specific task, it was only synthetic data. But I know that depending on other factors, you definitely might want to mix it or pre-train it and then fine-tune. And for some other neural networks in HoloLens too, we did mix real and synthetic. So I think Matt mentioned earlier how it's it can be much easier to collect a lot of real data. So for a different type of hand network that localized the hands in the image, we did a different technique, which was mostly real with some synthetic for some really hard cases. So it depends. There's never one straightforward, simple answer to that kind of choice.
Just getting back to a previous question as well, like one of the things Ankur had mentioned is that sometimes you have to hand tune knobs, right? Like in your simulator or data generator. Like, how do we ensure that no human bias creeps in? Because the moment you ask someone to provide their priors, you're injecting bias into it. Like, how do you make sure that we don't inject human bias into synthetic data, which is, what we're trying to prevent in the first place? I guess we can just let everyone answer this, because I assume everyone has their own opinions on this.
Thank you. We'll take one more question in the room and then maybe one online, and we will slowly wrap up. Okay, go for it.
What are the use cases where synthetic data was able to solve those use cases before? What are the use cases that are about to be solved with synthetic data? And what are the use cases that will be solved in years?
Okay, so let me rephrase the question. So what are the use cases that we can currently solve with synthetic data? What are the use cases that we think we will solve fairly soon with synthetic data? And what are the really hard use cases that we think we'll be able to solve in the future? So I guess kind of a ranking of difficulties here. Maybe online, Anchor, do you want to try this one?
Yes, so I think I would say, so maybe slightly controversial, but I think low-level vision is pretty much possible with scaling up synthetic data with the great rendering engines and simulators we have. And that involves, say, segmentation, pose estimation, optical flow, et cetera, et cetera. One of the other interesting things about scaling that up that you will get out of it is, imagine, things aren't working as expected for, say, a control task, but the low-level vision is still there. Then you can play back those scenarios in sim and then learn a control policy that is robust to those scenarios you've failed in while trying things in the real world. I feel like that's also one of the strengths of sim to real that you get out of it, that you can play back those scenarios in the simulator. I think that's something I personally feel is also very, very important, considering that it's not just computer vision that we need synthetic data for, but for downstream robotics and control tasks as well. So if you have a really good a low-level vision system that also works while the control task is failing, then you can play back those scenarios in sim and make your control task more robust to those failure cases. What was the other third question? Sorry, what was the third question?
The question was, what's the coming up successes of synthetic data? Like what we can do and what we can. I think
that's right. It's like a ranking of difficulty. So what we can solve right now, what we are about to solve, and what we will solve in the future.
So I think hand gestures is pretty much done with synthetic data. Landmark detection, we got it. I think pose estimation is coming up. Maybe things relating to the scene understanding can be done next in synthetic data. Well, what else?
What did you say was next?
Pose estimation, I think, is coming up, and scene understanding, action recognition.
Yeah, one question. Okay, sounds good.
I have one question actually specifically to Jonathan. So you use StyleGAN to synthesize data, but that StyleGAN is trained using real data. And we use that data that's been synthesized through StyleGAN and add it to our training set, and it improves the results. So where is this additional information coming from?
You're asking, sorry, I didn't get it.
So we have a generative model, right? And we learned that generative model using data that we have. Yes. And then synthesize more data from that generative model. And that still improves our downstream task. Let's say face recognition in your example. Where is the additional information coming from?
So when we generate the data in our synthetic pipeline, we don't use StyleGAN. We use we don't have a generative model per se. We use the graphics engine and things that artists generated, and a lot of procedural programming of 3D artists and programmers that do the pipeline. So it's not like that we're generating it using StyleGAN.
The editing that you were showing in this StyleGAN space, and that was just a data augmentation that you were adding on top of what existed?
The StyleGAN adaptation that we did is on top of it's after we invert the images that we generated without relying on real data. So the images that we did, they were relied on a very small amount of people who we scanned and other algorithmic approaches, but they're not based on FFHQ or some huge data set of people. The inversion algorithm that moves it into the StyleGAN code is obviously moving it. The realism is based on that additional data.
Thanks. So we are already way over time. So we'll probably wrap up the panel now. I wanted to thank all the speakers and panelists again. So please, a round of applause. Yes, thank you. And we wish to maybe to see you next year. We'll see if we do that again. Hopefully not hybrid this time, in person. Thank you.